Welcome to Professional C Programming Live Lessons. My name is Robert C. Secord and I'll be your instructor. I'm the manager of the Secure Coding Initiative and the CERT program of Carnegie Mellon Software Engineering Institute. The CERT program is a trusted provider of operationally relevant cybersecurity research and innovative and timely responses to our nation's cybersecurity challenges. The Secure Coding Initiative works with software developers and software development organizations to eliminate vulnerabilities resulting from coding errors before they are deployed. I'm also the author of several books, including 2 on C programming, Secure Coding in C and C++, 2nd edition, the CERT C Secure Coding Standard. I am a professor in the School of Computer Science and the Information Networking Institute at Carnegie Mellon University. I've been teaching secure coding in C and C++ to private industry, academia, and government since 2005. I'm very pleased that you decided to join me in these Professional C Programming Live lessons. My goal is to teach you things about C programming that you might not know and which you might never learn from on-the-job training. Most of the lessons will include some expository material, followed by examples in Microsoft Visual Studio 11. For each example, I'll compile and debug the program and discuss it in detail. In many cases, I will show you the corresponding assembly code for the x86-60 architecture and describe how often small changes in the program or how it is compiled affect the generated executable. I will also demonstrate code compiled and executed using the GCC compiler on Linux. In general, I prefer to demonstrate code using Visual Studio because it's more, visual. When you've completed these lessons, you learn to correctly perform common C language programming tasks that are frequently performed incorrectly, avoid programming errors that are not detected or reported by the compiler, and develop programs that are robust, reliable, secure, and fast. Let's talk about the lesson plan. Lesson 1 covers the topic of integer types. Integers are ubiquitous in C language programming, but their behavior is not well understood. This lesson discusses the use of signed, unsigned, and character types, as well as some specialized integer types. Lesson 2 covers integer conversions, including conversion rank, promotions, and the usual arithmetic conversions. Lesson 3 concludes our study of integers with a discussion of some common integer operations. In Lesson 4, we move on to a discussion of characters, arrays, and strings with an eye towards eliminating buffer overflows and other common string management errors. Lesson 5 describes 2 common memory models for string handling functions and some interfaces that implement them, including the new C11 Annex K bounds checking interfaces. Lesson 6 describes various compiler optimizations and how they can help you or hurt you. So thanks again for joining me in these live lessons. I hope you enjoy learning the material as much as I enjoyed making these videos for you. Lesson 1, Integer Types. Integers are ubiquitous in C language programming, particularly when you recall that the character types are also integer types. Unfortunately, the behavior of integers in the C language is poorly understood, even by experienced C language programmers. In this lesson, you'll learn about the representation, ranges, behavior, and uses of essential integer types in the C programming language, including unsigned integers, signed integers, character types, size t, pointer diff t, int max t, and uint max t. So next we're going to talk about unsigned integer types in C. C requires that unsigned integer types represent values using a pure binary system with no offset. So this means that the rightmost bit will have the weight 2 to the 0th or 1, and the next bit to the left will have the weight 2 to the 1st, and so forth. The value of the binary number then is the sum of all the set bits, with unsigned integer values ranging from 0 to a maximum that depends upon the size of the type. So that maximum value can be calculated as 2 to the n minus 1, where n is the width of the underlying type. So all bitwise operators will treat the bits using a pure binary model. So for example, If we took the value 13, which is represented as 1101, and we were to exclusive OR that value with the value 6, which is represented by 0110, 1 exclusive OR with 0 gives us 1, 1 and 1 gives us 0, 0 and 1 gives us 1, and 1 and 0 gives us 1. So the resulting value is 1011, which is equal to 11 as a pure binary number. Unsigned integers are also the natural choice for counting things, because when you're counting things, you'll start at having 0 of something and then count up to some positive number. So the standard unsigned integer types listed in non-decreasing length order are unsigned char, unsigned short int, unsigned int, unsigned long int, and unsigned long int. So non-decreasing length order means that unsigned char cannot be longer than unsigned short int, which cannot be longer than unsigned int, which cannot be longer than unsigned long int, etc. It is possible, however, for unsigned char to be the same size, for example, as unsigned long int on some specific architecture, even though that would be very unusual implementation. The different widths reflect existing hardware. So as time progressed, registers became larger and larger. So longer and longer types, such as the unsigned long int type, were introduced as needed. So the compiler and platform-specific integral limits are documented in the standard limits.h header file. It's important that you familiarize yourself with these limits, but you should remember that they are platform-specific. So for portability, you want to use these named constants and not the actual values in your code. So for example, uchar max is the C constant, which defines the upper range of the unsigned char type. C requires that minimally this value is 255, so that unsigned char types can represent values between 0 and 255. The x86-32 architecture also uses the same range, but it is possible that it could have a greater range. That's an implementation defined detail. So there are also constant expressions for unsigned short max, unsigned int max, unsigned long max, and unsigned long max. In most cases, the x86-32 architecture uses the same value as the C minimum magnitude. The one exception is unsigned int max, where the C minimum magnitude is a 16-bit value, and the x86-32 value is a 32-bit value. So because these are unsigned values, the minimum magnitude is always 0, and so no constants are defined for that value. You just simply use the value 0 in your code to represent the minimum value. So computations involving unsigned operands can never overflow by definition in the C language. So a result that cannot be represented by the resulting unsigned integer type, because again, integer types in C are models of the regular integer types. Those values are reduced modulo the number that is 1 greater than the largest value that can be represented in the resulting type. So for example, if we were using an unsigned char type with a maximum range of 255, the resulting value would be reduced modulo 256, and that value would be the result of the wraparound. So for addition and multiplication, that's really the same as pretending there are additional high order bits that are appended and to make sufficient room for the representation, and then those bits are discarded, and then the low order bits that can be represented in the type are the result of the operation. So this chart represents a 4-bit unsigned integer type. So if we start at the top of this chart with the value 0, and we increment that value by 1, we'll go clockwise around this chart until we reach the maximum value of 15 that can be represented as a 4-bit unsigned integer type. Now if we increment this value, we'll go from 15 to 0, which is the minimum size that can be represented in this type. So there's obviously a very sharp drop-off between the maximum value and the minimum value, and likewise if you take the minimum value and you decrement it, you go immediately to the maximum value that can be represented in this type. Okay, so we're going to look at an example of wraparound arithmetic using the x86-32 architecture on Microsoft Visual Studio. I've loaded Microsoft Visual Studio with a small sample program. This is the Visual Studio 11 Beta Ultimate version, which just recently came out. The full release is not yet available, but this should have all the latest features available from Microsoft. We'll look quickly at the property page for this program. First of all, I've enabled all warnings, so we'll try to build this code as cleanly as possible, and if there are diagnostics being issued by the compiler, I'll point those out. We've turned off optimization so that we can look at the assembly code and have some chance of understanding what the compiler is doing. And also, of course, on the Advanced tab, I'm compiling a C code. This, of course, is always a source of bemusement to the C Standards Committee that to build C programs using Visual Studio, you have to go to the Advanced tab and select C as an option. Okay, so let me cancel out of these and we'll go to the program. So the program's a very simple program. We're going to include some standard header files, and then we've got a main. And we're going to start by looking at the behavior of unsigned integer wrapping. So we'll stop here, go ahead and start debugging this program. So we're now on this line. We're assigning UI to this uint max value, which is the maximum value that can be represented as an unsigned int on this particular implementation. On x86-32, it should be this value of 4 billion something. So we'll single step through that assignment, we'll increment that value, and then we'll print out the result. So if we look at the output window, you'll see that printed out the value 0. So what's happened here is that once we were at the maximum value and increment, we have wraparound and we go to 0. So now we're just going to assign UI this value 0 again, although this is an unnecessary step because we've seen it already has the value 0. Then we're going to decrement it, and what we'll see now is that the decremented value here has the value of uint max. So we could look quickly at, let me stop debugging, and we could look quickly at what's going on in the assembly code. So start debugging again, and now we'll look at the assembly code. So here we're just moving uint max, which is represented by all bits set, into double word referenced by UI. We're then going to move that into the EAX register, which is a 32-bit register. We're going to add 1. And you can see now that the EAX register has the value of uint max, but after we add 1, that value again wraps around to 0. So then we'll store the result and print it. Then we can come back, and now we're going to initialize UI to 0, which again is unnecessary. It already has the value 0, but we'll then move that value into the EAX register. So you see EAX now has the value 0. We're going to subtract 1, and after we subtract 1 from 0, the value wraps around and we get the value of uint max. Unsigned integer expressions can obviously never evaluate to less than 0 because of wraparound. So it is possible in C or C++ to code tests that are always true or always false. In this example, I can never take on a negative value. So we assign I to some value n, and we decrement it, and we'll complete execution of this loop when I is no longer greater than equal to 0, which of course is impossible. So this kind of test is probably a coding error, but this wraparound induced infinite loop is not considered to be an error according to the language standard because it uses well-defined behavior of the language, which is that unsigned integer values will wrap around. So this would be viewed as compiler as an intentional attempt to code an infinite loop here. So whether or not it's actually an error depends on the particular algorithm's point of view. For counting things, wraparound is almost certainly an error. So you'll see that, for example, in some real-world issues that have cropped up. So for example, if you count it to 32,768 events, you probably don't expect the next event to be 0. So this occurred on December 25th, 2004, when Comair had to halt all operations and ground 1,100 flights after its flight crew scheduling software crashed. This software failure was the result of a 16-bit counter that limits the number of changes to a maximum of 32,768 changes in any given month. So there had been a number of storms earlier in the month, this being December, causing many crew reassignments, and the 16-bit value was exceeded and wrapped around. So to avoid unplanned behavior from wraparound errors, it's important to check for wraparound either before performing the operation or sometimes immediately following. The limits that we saw earlier from limits.h are helpful, but the naive use of these limits in code doesn't work. So we'll take a look at Visual Studio and see what we're talking about. So this is the same program we looked at earlier. We're going to step down to here where we're calling an unsigned int sum function in order to add two values together, in this case uint max and 1. So this is the definition of the function, and I've set a breakpoint here on the first line. So I'm going to clean it and then go ahead and rebuild it. And what I want to show you is that this project is building cleanly without any sort of diagnostics whatsoever, even though we've set the diagnostic at the highest warning level possible. So let's go ahead and start debugging this. So we're going to debug this program, and we're inside this addition. You can see that I has the value of uint max, and that the second operand j has the value 1. So we're going to single step, and you'll see that immediately we jump down to return I plus j, meaning that this conditional statement here evaluated to false. So we're going to perform the addition and return back to the calling function and print this out. If we take a look at the result, you'll see that the sum of those two numbers did in fact wrap around to 0, even with that test in place. So back to Visual Studio. We have next well, let's stop debugging and we'll go ahead and try to fix this problem. So the problem here, again, is that we have a test that just cannot happen. We're adding two values, two unsigned values, and testing if they're greater than uint max. That's impossible because this expression will wrap around before this test is ever made, so this is always going to evaluate to false. So I'm going to comment out this piece of code, and below I'm going to conditionally compile in this improved version of the test that now will test correctly. So what we've done here is, rather than saying, I plus j is greater than uint max, which will cause a wraparound, we've rewritten the test in such a way as to eliminate the possibility of wraparound. So we're going to test that I is greater than uint max minus j. So now j has to be in the range of 0 to uint max, which means that this expression uint max minus j can never wrap around. It has to have a value between 0 and uint max, depending of course on the value of j. So let's go ahead and set a breakpoint here and start over. So we're going to start debugging again, and of course the project's out of date because I made a modification. So now we're here on this revised unsigned int sum function, and the value of I is uint max, the value of j is 1. I'm going to go ahead and single step, and you can see now that we're stepping into the code. So rather than just jump directly to the addition, we've actually now detected the wrapping that's occurring, and instead of performing the addition, I'm just going to return uint max. Now, there's a number of things you can do once you've detected a problem. one solution is just to abort or print out some type of error message and abort. Instead of doing that, I'm implementing something called saturation semantics, which just means that once we've overflowed the maximum value possible, I'll just return uint max. It's not the correct answer, but it's closer to the correct answer than, say, 0 would be in this case. So this may or may not be appropriate. All depends on your system and how you want to detect and handle errors of this sort. So let me stop debugging, and we'll show you also what happens with taking the difference or subtracting two numbers. So I'm going to turn on this implementation of unsigned int difference, and I'm going to turn off this implementation, and we'll go ahead and rebuild the solution. So in this case, we do have a diagnostic issued, which is sort of interesting. So the first line of unsigned int difference, we're testing I minus j is less than 0. So this is another cannot happen condition. The problem, of course, is that if j is larger than I, this is never going to result in a negative value because they're unsigned numbers. It's going to wrap around, and we're going to wind up with a very large number. So in this particular case, at the highest warning levels possible, Visual Studio actually diagnoses this problem. It's sort of surprising that it diagnoses this problem and not the previous problem, but in fact it's not required to diagnose any of these, so the fact that we got a diagnostic here is just a bonus. So let me set a breakpoint here in the unsigned subtraction and go ahead and start debugging again. So now we're here to the difference, and the operands in this case are 0 for I and 1 for j. So subtracting 0 minus 1, of course, will result in wraparound. So we'll single step here, and we'll notice that again this test was unsuccessful. This test is always false, so we're just going to perform this operation. We're going to return I minus j back to main. So if we go to our output window, we'll see that the difference between those two values, 0 minus 1, is uint max. So let's go stop debugging, and we'll turn off the broken version of the unsigned subtraction function, and we'll enable the unbroken version and go ahead and rebuild the solution and set a breakpoint in the unsigned subtraction function. Go ahead and start debugging again. So here we have the same test. We're testing to see whether wraparound occurs, except instead of this previously flawed example where we invoked wraparound or allowed wraparound to occur in the expression, we've restated the test now to just say that if I is less than j, that means that wraparound will occur during this operation. So again, we'll return the saturation semantics. Instead of wrapping around to a very large number, we'll simply return 0. So I'm going to go ahead and single step through this, and you'll see now that this test has actually been successful. We've detected that wraparound is about to occur, and instead of performing the operation, we'll implement the saturation semantics and simply return 0. And you can see here in the output window that the difference is now given as 0. Okay, that's it for that. Now, wraparound will occur at different values depending on the specific implementation you're using. On some platforms, for example, in unsigned int, it might be a 16-bit value, and other platforms it might be a 32-bit value. So unless you're using exact width types such as uint 32T from standard int.h. The actual width used in the wraparound depends on the implementation, which again is going to vary from platform to platform. So unless that's taken into account by the programmer, it's likely that there will be a portability error. So here's a list of operations defined in C, including addition, subtraction, multiplication, division, remainder, etc. And there's an indication to the right of each operation whether or not that operation can result in wraparound. So arithmetic and subtraction we've already seen, or can possibly result in wraparound, as can multiplication. Division and remainder of unsigned values cannot result in wraparound, so those operations are safe from this particular condition. Previously, we covered unsigned integers, so in this sub-lesson, we're going to talk, obviously, about signed integers. So signed integers are used to represent positive and negative values, the range of which depends on the number of bits allocated to the type and the representation. In C, each unsigned integer type, except for bool, has a corresponding signed integer type which occupies the same amount of storage, and that relationship is guaranteed by the C standard. Standard signed integer types include signed char, short int, long int, and long int. And these types are again listed in non-decreasing length order, meaning that signed char cannot be longer than short int, which can't be longer than int, which can't be longer than long int, etc. So except for char, the sign can be omitted. The problem with char is that signed char, unsigned char, and char are all three distinct types, and the only way you can be guaranteed that you're getting a signed type is to include signed char. Plain char is implementation defined to be either signed or unsigned. The int can also be omitted unless it's the only keyword present. All sufficiently small non-negative values have the same representation in the corresponding signed and unsigned types, which is the pure Boolean representation. The signed bit is treated as the highest order bit and indicates whether the represented value is positive or negative. The C standard permits negative values to be represented as either signed in magnitude, 1's complement, or 2's complement values. All three methods are in use in various platforms, although on desktop systems, 2's complement is the most prevalent representation today. Sign in magnitude uses the high order bit to indicate the sign, so a 0 indicates a positive number while a 1 indicates a negative number. Other non-padding bits represent the magnitude of the value in pure binary notation, the same as for unsigned values. To negate a sign in magnitude value, you just simply toggle the sign bit. So here we've got the value 41 represented in a pure binary notation, and the sign bit is 0, indicating that this is a positive value. To create the negative value, we keep the same representation for the magnitude of the value and simply flip the sign bit to 1, indicating that this is now a negative value. 1's complement, the sign bit is given the weight negative 2 to the n minus 1 minus 1, and the other value bits have the same weights as for unsigned. So for example, this bit string equals negative 43 in 1's complement representation. Given a width of 10 bits, the sign bit has the weight negative 2 to the 9th minus 1, or negative 511. The remaining bits add up to 468, so that 468 minus 511 equals negative 43. When 1's complement or sign magnitude representation is used, the lower bound is negative 2 to the n minus 1 plus 1, while the upper bound is 2 to the n minus 1 minus 1. To negate a 1's complement value, you simply toggle each bit, including the sign bit. So, for example, each 1 is replaced with a 0, each 0 is replaced with a 1, and even the sign bit is reversed. And this forms the 1's complement or negative representation of this value. In 2's complement, the sign bit is given the weight 2 to the n minus 1, and the other value bits have the same weights as for unsigned. So for 2's complement, this bit string equals negative 43. So given a width of 10 bits, the signed bit has the weight negative 2 to the ninth or negative 512. The remaining bits equal 469, so that 469 minus 512 equals negative 43. To negate a 2's complement value, you first form the 1's complement negation and then add 1. So here we take an original value, positive value, we form the 1's complement negation, and then we add 1, and we end up with this value, which is the resulting 2's complement representation. So here's a wheel which shows a 4-bit 2's complement representation. And so we'll start with 0 in the high noon position. And as we go clockwise around this wheel and increment the value, we'll increment up to the maximum value that can be represented in this 4-bit signed integer type, which is 7. So all the magnitude bits are set, but the signed bit is still clear. If we increment one step further, we go directly from the maximum value that can be represented in this type to the minimum value that can be represented in this type, which is negative 8. So as we increment around the wheel, the value becomes increasingly less negative till we reach 0, and then as we continue around, we'll eventually once again reach the maximum value that can be represented in this type. So this chart shows the binary and decimal representations for an 8-bit 2's complement signed integer type with no padding. The first bit representation is all zeros, and this equals the decimal value 0. If we increment this, we get this bit pattern with the 1 in the rightmost position. That's equivalent to 2 to the 0 or decimal 1. So we can then increment through the various bit patterns till we get till 126 and 127. 127 is the maximum value that can be represented in this number of bits in the 2's complement representation. So you can see that the signed bit is still clear, but all the other bits are set. This value is equal to 2 to the n minus 1 minus 1. And it's also represented by the constant s char max, which is the maximum value that can be represented as a signed character on this particular implementation. When we increment again, we wind up with 1 in the signed bit and then all zeros. And this is the value negative 128. And this is also the character constant s char min, which is the minimum value that can be represented as a signed char on this implementation. So again, you'll see that starting at the maximum value and incrementing by 1 brings us to the minimum value that can be represented in this type. So as we increment further, we'll iterate through the remaining negative values to the less negative values, negative 2 and then negative 1. And you can see that negative 1 is represented by all bits set. So this chart compares signed in magnitude 1's complement and 2's complement representations, assuming an integer with a width of 10 bits and ignoring padding. So what you'll see is, first of all, that signed in magnitude and 1's complement both have positive and negative representations for 0. However, the 2's complement representation only has a positive representation for 0. It does not have a way to represent negative 0. So at the top end of the scale, you'll see that signed in magnitude and 1's complement have no way to represent the values 512 or negative 512. However, in 2's complement, you can in fact represent the value negative 512, but you cannot represent the value 512. The reason for this is that one of the positive representations is used to represent the value 0, but all the bit patterns available in the negative space are available to represent values. So we can represent one more value in the negative space than we can in the positive space. So signed in magnitude and 1's complement again have two representations for the mathematical value 0, normal 0 and negative 0. The negative 0 representation can be produced by logical operations, but is not allowed for the result of any arithmetic operation unless one of the operands had a negative 0 representation to begin with. On a computer using 2's complement arithmetic, a signed integer type ranges from negative 2 to the n minus 1 through 2 to the n minus 1 minus 1. When 1's complement or signed magnitude representations are used, the lower bound is 2 to the n minus 1 plus 1, while the upper bound remains the same. So the C standard mandates minimum widths for the standard signed integer types. Signed char must be represented by a minimum of 8 bits, short 16 bits, int 16 bits, long 32 bits, and long 64 bits. Implementations can use a larger number of bits to represent these values, but they cannot use fewer bits to represent these values. The actual widths for a given implementation can be inferred from the maximum representable values defined in the limits.h header file. The sizes, meaning the number of storage bytes for each of these types, can be determined with the size of type name, and this size will include any padding bits, if any. So the minimum and maximum values for an integer type depends on the type's representation, whether it's 1's complement, 2's complement, sign and magnitude, the signedness, whether it's signed or unsigned, and the width of the underlying storage. So this chart shows the ranges for signed integer values. The left-hand column shows the constant expression that's used to represent various values, such as schar min and schar max, the minimum and maximum values that can be represented as signed character. There's also constants for short min and short max, int min and int max, long min and long max, and long min and long max. So let's look at signed char again. You'll see that there's, in the second column, this is the C mandated minimum magnitude. So this is the minimum range of values that must be supported by an implementation. So for signed char, the range is -127 to +127, which allows for 1's complement and sign and magnitude representations. However, the x86-32 architecture uses a 2's complement representation, so it can represent negative values up to -128, which is 1 greater than the range required by the C standard. However, the upper bound, the maximum value of +127, is the same, and you get similar results for other types. So this chart shows the range of integer types for x86-32 architecture. This chart is very definitely not to scale, but you can see that the range of assigned char type is -128 to +127. Unsigned char is 0 to 255. Short is -32,768 to +32,767. And unsigned short is 0 to 65,535. What becomes very apparent on this chart is that not all values that can be represented by a signed char type can also be represented by an unsigned char type. Likewise, not all the values that can be represented by an unsigned char type can be represented as signed char type. So you can see that it's not very easy to convert values from one type to another, because frequently the value cannot always be represented in the corresponding type. So it is always safe to convert from a smaller type of a particular signedness to a larger type of the same signedness. So for example, conversions from signed char to signed short are always safe. So overflow occurs when a signed integer operation results in a value that cannot be represented in the resulting type because of the lack of precision of the type. So here we've got a little comic that shows presumably a C programmer who's trying to fall asleep by counting sheep. He gets to 32,767 where an overflow occurs, and now all of a sudden the next number is -32,768. So signed integer overflow is undefined behavior in C. This allows implementations to really implement any behavior they want, but typically what will happen is that C implementations will silently wrap, trap, or some combination of the two. So because signed integer overflow produces a silent wraparound in most existing C compilers, some programmers assume that this is well-defined behavior, but in fact it's not. And because it is undefined behavior, the compiler can do whatever it wants and frequently will use this as a reason to perform various optimizations that may or may not be desired. So we're going to shift to Visual Studio and we'll see an example of overflow in Visual Studio. So I've got here a very simple program that includes some standard header files and has a main. And we have a breakpoint set on the first line where we're going to assign int min to this integer variable si. So let me go ahead and build the solution, and we'll go ahead and start debugging. So we're now stopped on the first line, and we're about to initialize this signed integer variable to int min. This value should be negative 2 billion something on an x86-32 platform. So we'll single step, and you'll see now that si has been initialized with this value. Now we're going to decrement it starting at int min, and when you do that, we wind up going to int max. So we went from the most negative value that can be represented in this type to the maximum value that can be represented in this type. Similarly, if we initialize si to int max, so here we have si now int max, and we increment this value, we're going to wrap around to the minimum value that can be represented as this type. So you can see that at least for addition and subtraction on this particular implementation, the result is the values will silently wrap around. So overflow, signed integer overflow, can cause a variety of problems. One is the undefined behavior, but also even for implementations where the values silently wrap around, sometimes that can produce unexpected results. So for example, the negative of 2's complement's most negative value for a given type cannot be represented in that type. So this is because the 2's complement representation is asymmetrical, with the value 0 being represented as a positive number. So for example, a programmer might decide to implement an absolute value function where it takes a single argument n and tests to see whether n is less than 0, and if it is, it negates the value and returns the negated value, or otherwise it just returns the value as is. So this seems perfectly fine, and this will work correctly for all values except for the most negative value in the type, in which case this has undefined behavior and returns a result which is presumably wrong or unexpected. So let's say, for example, that n is a signed character type on a platform that has a range of negative 128 to positive 127, and we call this absolute macro with the value negative 128. What will happen is we'll test to see if negative 128 is less than 0. It is, so we'll negate it and return the negated value of negative 128. However, positive 128 cannot be represented as a signed character type. So instead, this function will actually return the value negative 128. And so having an absolute value function return a negative value is likely to be unexpected by most programs and by most programmers. So this chart shows operators that can overflow in C. And you'll see that addition and subtraction and multiplication again can overflow. This is similar to unsigned arithmetic. But of note is that division and remainder operations can also overflow on 2's complement representations. And we'll see more about that in a future sub-lesson. For the next sub-lesson, we're going to discuss character types. Character types in C are actually integer types. However, compilers do have the latitude to define the plain char type to have the same range, representation, and behavior as either signed char or unsigned char. So what this means is that when you declare something char, you don't really know for certain if it's going to be a signed or unsigned char. Especially you don't know that in a portable way, because as soon as you take even if your implementation defines it to be, say, signed, when you port that to another implementation, it may be defined to be unsigned char. So we're going to look at an example where the char type variable C may be signed or unsigned, and we'll do that in Visual Studio. So this is a really simple program, and all we have is a main. We have a variable char C, which is being initialized to 200, and then we have an int I that's being initialized to 1000, and then we're going to divide I by C and print the result out. So let's go ahead and I'm going to do a clean build to start out with. So I'm going to clean the solution, and then we'll build the solution. And what I want to do here is check for errors, and it looks like there are no errors. We had a clean build. So if we take a look at this code, well, let's go ahead and I'll set a breakpoint right away, and let's delete this other breakpoint, and we'll go ahead and start debugging. So I'm going to go ahead and initialize C. So C takes on a value of -56, which is sort of interesting. So by default, char on Visual Studio is a signed type, and it has a range of -128 to +127, which means that this value 200 is outside the range of values that can be represented as a signed char type. So this is actually undefined behavior. Now the compiler should have diagnosed this, but you notice that it did not. So what it basically did was it reduced this modulo 128 until it could be represented in a signed char type. So it wound up assigning variable C the value -56. So we're going to continue. We're going to assign int I 1000. 1000 is easily within the range of assigned int type. And now we're going to perform the division. And if I skip to the output window, you can see that the result of this division of 1000 by 200 turns out to be -17, and that's because of the truncation that takes place when we're trying to assign this value 200 to a signed char type. Okay, so I'm going to go ahead and stop debugging, and now we're going to do something different. So we're going to go into the project page, and I'm going to add an additional option here, which is the J option. Now the J option on Microsoft Visual Studio says to treat char as an unsigned type. So let me go ahead and clean the solution and rebuild the solution, and we'll go ahead and start debugging again. And we'll take a quick look. I don't expect there to be any diagnostics, and there are not. So go ahead and start debugging again. And let me go ahead and single step through the initialization of C. You'll see C now has not the value -56, but the value 200, because C is now being treated as an unsigned char, which has a range of 0 to 255. So 200 is within the range of that type. So I'm going to go ahead and single step. We'll initialize I, and then we'll perform the division. And if I go over to the output window again, you can see clearly now that the result of this decision is 5. And so the result here is clearly dependent on an implementation defined detail of whether or not char is a signed or an unsigned type. And that's probably, or well, it could be a portability issue. So the best thing to do is to be specific. So we're going to explicitly make char an unsigned type. And let's go back to the properties page. I'm going to remove this property. So this will go back to the default that char is a signed char type. And let's go ahead and build this solution and go ahead and debug it. So you'll see now that C is getting the value of 200 because this is explicitly an unsigned type. And when I do the division, we'll now get the expected result of 5. So what we've done is we've eliminated the implementation defined behavior from this program by declaring char explicitly as unsigned char, and now we're always guaranteed to get the same behavior. So the problem is, of course, that it's very difficult to reason about the correctness of a program without knowing if these char types are signed or unsigned. By declaring the variable C as an unsigned char, The subsequent division operation is independent of the signedness of char and consequently has a predictable result. So we do have a guideline in the CERT-C secure coding standard called int 07C, use only explicitly signed or unsigned character types for numeric values. And what this does is it recommends that you use signed char or unsigned char if you're going to be representing integer values and not characters. So signed char can portably represent values between -127 and +127, or unsigned char can portably represent values between 0 and 255. And this is really the only portable way to guarantee the signedness of the character types. So this is part of the CERT-C secure coding standard, and you can see this rule here in 07, use only explicitly signed or unsigned character types for numeric values. There's a description of the rule. There's some references to related rules, and then you'll see some non-compliant examples, some compliant solutions, exceptions to the rule, and some assessment of the risk involved in violating this rule, some automated tools that can be used to detect violations of this rule, related vulnerabilities, related guidelines, etc. So that's available up on our website at www.securecoding.cert.org. In this next sublesson, we're going to talk about another integer type, the size t type. So C defines additional integer types in the standard int types, and the standard def, standard headers. These include the extended integer types, which are optional implementation defined but fully supported extensions, which, along with the standard integer types, makes up the general class of integer types available for a particular implementation. So identifiers, such as whatever underbar t defined in the standard header files, by convention are all type defs, which means that they are synonyms for existing types, not new types. So despite the name, no type def has ever defined a new type. Type def names required to be defined as integer types by standard headers can be synonyms for either standard integer types or for extended integer types. Size t is the unsigned integer type of the result of the size of operator and is defined in the standard header standard def.h. Variables of type size t are guaranteed to be of sufficient precision to represent the size of an object. So unlike int and short and long, which are mostly there to map to available register and word sizes, variables of type size t are defined to have a semantic meaning, meaning that they can represent the size of an object. The limit of size t is specified by the size max macro. Now, size t was not included originally in KNRC, which is why many developers are not familiar with it, don't use it appropriately, or use it erroneously. So the C Standards Committee introduced size t to eliminate a portability problem. On some platforms, it's appropriate to use unsigned int to represent sizes, but it may be too small to represent the size of the address space on other platforms. Similarly, the unsigned long type might be used to represent the size of objects, but it might be too large on some other platforms and consequently inefficient. So the portable and efficient way to declare a variable containing a size is size t n equals size of something. So to declare that variable as type size t. Similarly, the portable and efficient way to define a function foo that takes a size argument is to declare that argument as type size t. So functions with parameters of type size t often have local variables that count up to or down from that size and index into arrays. And size t is frequently a good type for those variables. Also, variables that represent the count of elements in an array should be declared as size t, particularly for character arrays, where the element count can be as the largest object that can be allocated for that system. So let's look at an example. So I have a program here which was built for the x86 64-bit platform. So I'm going to go ahead and start debugging this, and what we'll do is we'll stop on the very first line, and I'll single step through this program and describe to you what the program does. So the very first line, we declare a variable of type size t, which again, because this is compiled for the x86 64-bit platform, this will be an unsigned 64-bit integer type. So we're assigning this initially to uint max divided by 2 plus 100. The reason I'm doing this is to create a value which is slightly larger than int max. So let me single step through this program. We declare a pointer p, which is a pointer to a character, and we declare a pointer str, str, and we initialize that to the return value from calloc. So calloc is being called with 2 arguments. Tainted int is the size of the element to allocate. It's this very large number that we've just created. So I'm going to go ahead and single step, and we'll see that calloc has in fact succeeded and returned a non-null value. That is unlikely to be true if this were built on a 32-bit platform. So we're now going to stir copy hello world into stir, and we can be reasonably assured that that's not going to result in a buffer overflow because we've allocated a massive string and we're just copying a very small string into it. So next we're going to step into this copy function. So this copy function is used to make a copy of the array that we just allocated. It takes 2 arguments. The first is the size of the array, and this is appropriately declared as a variable of type size t. And the second argument is a pointer to the array to copy. So let's single step through this. The first thing we do is we make sure we're not performing a 0 size allocation because those are implementation defined and sometimes have unexpected behavior. Next, we're going to allocate storage for the copy, and for this call we just call malloc because there's no need to initialize this storage. We're going to immediately copy the storage from stir into this space. So that call succeeds, and now we've got to kind of the core of this function, which is to copy from the source array referenced by stir to the destination array referenced by p. So I'm going to show you the assembly code. Well, let me show you something else first. So this variable I is actually declared here as an int. So on this platform, signed int is a 32-bit signed value. So we're performing a comparison here between I, which is a 32-bit signed value, and n, which is a size t value, which is declared to be a 64-bit unsigned value. So in order to do this, we have to convert I into a 64-bit unsigned value so we can compare apples and apples here. When we look at the assembly code, we'll basically see this happening. So if you look at this instruction here, we're moving the double word value referenced by I into the RAX register, which is a 64-bit register. So a word on Intel platforms is 16 bits, so a double word is a 32-bit value. So we're moving a 32-bit value into the 64-bit register, and the move SXD command is going to propagate the sign bit up to the high order 32 bits. So this is necessary because I is assigned int, and we want to preserve the value when we convert it to a 64-bit register. So the next instruction here is simply doing a comparison between the value of I sign extended to 64 bits and the quad word referenced by n. So n again is a 64-bit value. So we compare these two values, and then based on this comparison we'll determine whether or not this loop is completed. So we'll go back to the loop, and I'm going to start to single step through the loop. And if you look down into this window below, you'll see that as I increment through this loop, that the hello world string referenced by stir is being copied to the storage referenced by p. So it sort of looks like this storage at stir is disappearing, but really what's happening is we're simply incrementing the pointer as we walk through memory. So this loop is going to iterate quite a few times, as you can see by this value of n. So rather than single step through this for the rest of my life, I'm going to just say continue. And we're now going to execute until this return statement and the loop has completed. So if we look briefly here at I, we see something sort of unusual, which is that it has this negative value. So what's happened, of course, is that because I is a signed int, it has a maximum value of int max. So once we reach the value int max, and it still compares less than n, because n is greater than int max, I will then be incremented, and it will become int min. So once it becomes int min, it will be converted to a 64-bit positive value to be compared with n, and because it's now a negative number, it'll actually be converted to a very large positive number, which in this case is now greater than n. So this loop will terminate. So that means that, in fact, this code is erroneous because the loop terminated before we copied the entire object from stir to p. So let me go back to PowerPoint and talk about what was just happening. So one of the interesting aspects of this program is that the behavior of this code is implementation defined. And the relative sizes of the size t type and the int type influence the behavior of the code. So for example, on x86-64, which is the platform we were just looking at, the size of size t is greater than the size of int. But on other platforms, such as x86-32, the size of size t is the same as the size of size int. And this will influence the behavior. So for example, on the platform we just looked at, the x86 64-bit platform, where the size of size t is greater than the size of int, for values of n between 0 and int max, the loop will execute n times as expected. So that's both good and bad. It's good because it works, but it's bad because it might fool you into thinking that the code is correct when in fact it is not. So for values of n between int max and the value of int min converted to a unsigned type, the loop will execute int max times. However, once I becomes negative, the loop will stop and I will remain in the range of 0 through int max. So this is the case that we just in fact looked at. Also, for values of n between the value of int min converted to a unsigned type and size max, I will wrap and take on a range of values which will actually result in the loop overriding memory outside the bounds of the object. So this is even more of a disastrous case because writing to random areas of memory is undefined behavior and quite dangerous. On a 32-bit platform where the size of size t is the same as the size of int, the unsigned value n may still contain a value greater than int max. And the reason for this, of course, is because size t is an unsigned value. It has a greater positive range than a signed value of the same size, which has roughly half the range. So, assuming quiet wraparound on signed overflow, which is true for x86-32 platform, the loop will execute n times because the comparison between I and n is again an unsigned comparison. Once I is incremented beyond int max, I will take on negative values starting with int min. Consequently, memory locations referenced by p sub I will precede the memory referenced by p, and a series of writes outside the bounds of the array will occur, again resulting in undefined and dangerous behavior. So if we go back real quickly to Visual Studio, we'll see that the entire problem here is caused by declaring this variable I as an int. So if we simply declare this as size t, all the problems and all the complexity go away because now n is the same size as I, and so there are no conversions that need to take place in this comparison, and each of these variables is completely able to fully represent the size of the object that we're working on. Okay, to wrap up integer types, we're going to discuss a few more integer types that you should be aware of: pointer diff t, int max t, and uint max t. So pointers may be subtracted when both pointers point to elements of the same array object, or one past the last element of the array object. The result of the subtraction is the difference of the subscripts of the two array elements. The size of that result is the implementation defined, and its type is a signed integer type called pointer diff t, which is defined in the standard def.h header. There is the possibility that the result of subtracting pointers to elements of the same array cannot be represented in an object of that type, and in those cases the behavior is undefined, but that is very uncommon and will occur only when dealing with extremely large arrays. The lower and upper limits of pointer diff t are defined by the pointer diff min and pointer diff macros respectively. So few programmers consider the issues around formatted I/O and type definitions. A programmer-defined integer type might be any type supported by an implementation, even one that's larger than unsigned long. So for example, an implementation that supports 128-bit unsigned integers and provides a uint fast 128t type, a programmer might define a type def that looks something like this, where they'll type def uint fast 128t to be my type def underbar t. The definition of this programmer-defined type may change in the future, which creates a problem when these types are used with formatted output functions such as printf and formatted input functions such as scanf. So the C standard defines the int max t and uint max t types, which are integer types with the greatest width and are capable of representing any value representable by any other integer type of the same signedness. So int max t can represent any signed integer types on a given implementation, and uint max t can represent any unsigned integer types on a given implementation. So this capability allows conversion between programmer-defined integer types of the same signedness and int max t and uint max t. So for example, if we have a user-defined type my type def underbar t, which could be any type, but let's say it's a 128-bit type, and we have another variable temp, which we've defined to be a uint max t. So we do know that my type def t is definitely an unsigned type. So in this case, the conversion from x to temp from a type of my type def t to uint max t is always okay, because the uint max t can represent any unsigned integer type on this implementation. However, going back the other direction from temp to x is not necessarily safe, because uint max t could be considerably larger. So before making this assignment, we have to check that the temp variable of uint max t type is not larger than the maximum size supported by the my type def t type. So formatted I/O functions can be used to input and output greatest with integer type values using the JLength modifier. So the JLength modifier in a format string indicates that the following conversion specifier of one of these types will apply to an argument with type int max t or uint max t. So these types can be used for formatted I/O on programmer-defined integer types. So for example, we could call printf with %ju. U indicates it's unsigned, and j indicates it's one of these greatest size types. And we'll take x, which is a variable of my type t, and we'll cast it to uint max t, making sure it's the same size as is expected by this format conversion. So this conversion again is always guaranteed to work, because uint max t
can be used to represent any unsigned integer type on this platform.
So in summary, you want to select an appropriate integer type based on the range of values that you plan to represent. Unsigned integers, of course, are a natural choice for counting things where you're not going to have any negative values. You can start from 0 and count to some positive value. Any variable or argument that's going to store a size should be declared as type size t. And of course, variables that can represent both positive and negative values must be signed. So it's not necessary to assume the minimum magnitudes defined by the C standard. Not all C programs are strictly conforming and maximally portable. What you do want to do is understand the ranges supported by your target platforms, and most importantly, document your assumptions, preferably using static assertions, so that if that software is ported to a platform where your assumptions are no longer valid, the compiler will generate an error message and let you know that there's a portability issue. Integer conversions are generally poorly understood by C programmers. These conversions can occur explicitly as a result of a cast or implicitly as required by an operation. While conversions are generally required for the correct execution of a program, they can also lead to lost or misinterpreted data. In this lesson, you'll learn the rules governing integer conversions in the C programming language, including conversion rank, promotions, and the usual arithmetic conversions, conversions to unsigned types, conversions to signed types.
Type conversions in C can occur explicitly as a result of a cast or implicitly as required by any particular operation. Implicit conversions occur when operations are performed on mixed types and a value needs to be converted to an appropriate argument type. So for example, we can add an unsigned char integer type and a signed integer type and store the result in a short int in the C language, and the compiler makes all the necessary conversions to make sure this operation just works. So this appears to be a very natural thing for C programmers to do, when in fact we're really operating on apples and oranges here, and there's a bunch of implicit conversions that need to take place in order to make this operation happen, and that's all again performed by the compiler. So the way this is done involves three concepts: integer conversion rank, integer promotions, and the usual arithmetic conversions. So each integer type has an integer conversion rank that helps determine how conversions are performed. The integer conversion rank provides a standard rank ordering of integer types that's then used to determine a common type for computations. So the integer conversion rank rules are not very difficult. First of all, no two signed integer types can have the same rank even if they have the same representation. So the rank of a signed type is greater than the rank of any signed integer type with less precision. So that means, for example, that the rank of long int is greater than the rank of long int, which is greater than the rank of int, which is greater than the rank of short int, which is greater than the rank of signed char. The rank of any unsigned integer type is equal to the rank of the corresponding signed integer type. So for example, the rank of unsigned short int will be the same as the rank of short int. The second concept is integer promotions. An integer promotion states that an object or expression with an integer type other than int or unsigned int, whose conversion rank is less than or equal to the rank of int or unsigned int, can be used in place of any expression where an int or unsigned int may be used. So the integer promotions are applied as part of the usual arithmetic conversions, which we'll talk about shortly. There was a divergence in the C language that needed to be resolved by the C89 Standards Committee. So some implementations took what's referred to as the unsigned preserving approach, which called for promoting the two smaller unsigned types to unsigned int. The second approach was called the value preserving approach, and this stated that if all values of the original type can be represented as an int, the value of the smaller type is converted to int, otherwise it's converted to unsigned int. So for example, if you were on a platform where unsigned char was an 8-bit value and signed int was a 32-bit value, it's very easy to represent all the values that can be represented as an unsigned char as a 32-bit signed int. So on those platforms, the unsigned char value would be converted to signed int. So the C89 committee decided in favor of the value preserving rules, so that's the way the C language behaves today. So the purpose of integer promotions is to avoid arithmetic errors from the overflow of intermediate values, and also to perform operations in a natural size for the architecture, which is what the signed int type is. So I've got again a very short program, and I have two examples, so I've broken them out into separate functions so that we can look at each one independently. I'll do a clean solution, and I'll do a build, and this way I can show you down here that there's nothing up my sleeve. There's no diagnostics that have been issued for this program, so this program has built cleanly. So we'll start debugging. And I've set a breakpoint here in the first example, which is a short expression using some signed char variables. So we have C1, C2, and C3, and we're going to multiply C1 by C2 and then divide by C3. So each of these variables has been assigned a value. Typically, these will come from external data sources, so we won't know what the values are ahead of time, but this is for explanatory purposes. And so if we have C1 set to 100 and C2 set to 3, we're going to multiply these two values together first and end up with 300 divided by 4. So if you look at the value 300, and we're on a x86-32 platform, where signed char has a range of -128 to +127, you can see that this value 300 exceeds the range of +127 of the signed char type. So there's an expectation here that this value is going to overflow, and the result of this arithmetic operation is going to be incorrect. So this is where integer promotions comes to save the day. So we'll look at the assembly code for this expression, and you'll see the first thing that happens is that we're going to move the value for C1 into the EAX register. So you can see that C1 is being referenced as a byte, so as an 8-bit value on x86-32 architecture, and it's being moved into the EAX register, which is a 32-bit register. So you can see already that we're promoting from 8-bit to a 32-bit signed type. And the instruction is the move SX. That's because the C1 is a signed value, so as we move it into a 32-bit register, we want to extend the signed bit into the high-level bits, so we preserve the signed value in the EAX register. So similarly, we're going to put C2 into the ECX register, then we're going to multiply these two values together, and then we're going to move the value stored in C3 into the ECX register, and then we issue a CDQ instruction, which is going to extend these bits into the EDX register and perform the division. And following the division, and you can see again that the division is producing a 32-bit result. So we then move the result of the AL register, which is the low order 8 bits of the EAX register, into the resulting value. So what's happened here, let's go back to the source code. I'll perform this operation, evaluate the expression, and you can see down here that the result stored in C result is 75. So instead of having overflow from this intermediate value, the integer promotions have promoted each of these operands to signed in type, and the operation is performed as a 32-bit operation instead of being performed as an 8-bit operation. And it's not until the last store where the value is truncated back into the range of C result or signed char. And so as a result of that, we do in fact get the correct result from this operation, which is 75. So let me go on to the next example. So the second example, we're going to just complement an unsigned char value. So you see here we have unsigned char type UC, and we're initializing it to uchar max, which has the value of FF. So we're going to take the complement of this value, meaning we're going to just flip all the bits. So the result of this operation depends on, well, programmers can have different expectations as to what the result of this expression will be. But the standard states quite clearly what the result must be. So it's not uncommon for a programmer to look at this and think, well, I've got all the bits set here, so when I complement this value, I'm going to end up with all the bits cleared or the value 0. But let's take a look at the assembly again. And so you can see the first instruction here. We're going to move the value from UC into the 32-bit EAX register. So the instruction used is move ZX, which means that it's going to clear the high order bits in the EAX register because UC is an unsigned type, and we don't want to end up with a very large unsigned value. So we're going to then take the complement, and you can see this NOT instruction is being performed on the EAX register, which is a 32-bit register, and then we're going to store the result back into I, which is a 32-bit value. So again, what's interesting here is that when we move UC into EAX, we're going to clear the high order bits. So let's go ahead and single step through this. So we're going to move the value into I, and we're going to then complement the result and then move it back into I. And so you can see down here that I now has the value negative 256. So this could be a little bit surprising to programmers that expect to wind up with 0 because we started with all bits set. But what they're failing to account for are the integer promotions. The third step in determining how conversions are applied is the usual arithmetic conversions. So these are a set of rules to yield a common type for both operands of a binary operation or the second and third arguments of the conditional operator. Balancing conversions will always involve two operands of different types. One or both operands may be converted as a result of the usual arithmetic conversions. So most operators in C and C++ that accept integer operands will perform conversions using the arithmetic conversions, including multiplication, division, remainder, addition, subtraction, and various comparison operators and other arithmetic operations on integer types. So the usual arithmetic conversions are a little bit complicated, so we'll step through this carefully. As I go through each step, as soon as a step applies, the process is completed. So the first step is to determine if both operands have the same type. If both operands have the same type, no conversion is necessary and we're done. If they don't have the same type, obviously they have different types. So if both operands are of the same integer type, for example, signed or unsigned, the operand with the type of the lesser rank is converted to the type of the operand with the greater rank. So if we continue, that now means they have different types. One is signed and one is unsigned. So if the operand that has unsigned integer type has a rank that's greater to or equal to the rank of the type of the other operand, the operand with the signed integer type is converted to the type of the operand with the unsigned integer type. And so it's quite common when you're operating on an unsigned and a signed type to end up with an unsigned type. And some people, so common in fact that some programmers think that that is always the result. However, if the type of the operand with the signed integer type can represent all of the values of the type of the operand with the unsigned integer type, the operand with the unsigned integer type is converted to the type of the operand with the signed integer type. So that's similar to the value preserving rules, and it results in an operation on a signed and unsigned type resulting in a signed integer type. And finally, if none of these previous rules apply, both operands are converted to the unsigned integer type corresponding to the type of the operand with the signed integer type. So the C standard defines conversions in terms of the signedness of the converted to type. So we'll look first at conversions to unsigned types, and then we'll look at conversions to signed types. So for conversions of unsigned to unsigned, these are the easiest to understand. Conversions of unsigned integer types to a type with a larger width is always safe, and it's accomplished simply by zero extending the bit pattern. Conversions occur implicitly as part of the usual arithmetic conversions for unsigned integer operands of different widths. The result of each operation has the type and representation range of the wider of the two operands. So provided that the corresponding mathematical operation produces a result within the representable range of the resulting type, the represented value is the correct mathematical value. So for conversions of an unsigned integer type to an unsigned integer type of a smaller width, the value is reduced 2 to the w, where w is the width of the smaller type. So this corresponds to truncating the high order bytes in the resulting bit pattern. We have here a really simple program, and I'll go ahead and compile this at warning level 3, which is the default warning level for this version of Visual Studio. And we'll do a build, and you can see that the build cleanly. But if I do increase the warning level to warning level 4, you'll now see that when we do the build, we are going to get a diagnostic message which says that initializing conversion from unsigned int to unsigned char, possible loss of data. So we do get a diagnostic at the higher warning levels, which is why it's always a good idea to use the higher warning levels, but again, the compiler is not required to issue a diagnostic, and other compilers might not do so. So let's take a look at this code. Again, this is a really simple program. We have an unsigned int, so this is a larger type, and we're initializing it to the value 300. Clearly, 300 is within the range of representation of unsigned int on any standard conforming program. And we're going to simply assign the value stored in UI, which is 300 at this point, to the variable UC, which is of type unsigned char. So unsigned char on this platform has a range of 0 to 255, so this operation is going to have to result in truncation of the larger value. So the standard basically says that for this platform, the width of unsigned char is 8 bits, and so the standard requires that the value 300 is reduced modulo to the width of the type, which is 8. So this means that 300 is going to be reduced by 2 to the 8th, or 256, and this should give us a resulting value of 44. So we'll go ahead and start debugging, and we're on this line, we're about to assign the value stored in UI, or 300, to UC. So let's look at the assembly code. So what's happening here, there's no operation, we're just moving data from one variable to another. So we're going to take the value stored in UI, and specifically we're going to take the low order byte of the value stored in UI and move it into the AL register, which is the low order 8 bits of the EAX register. And then we're going to take that value and simply store it into the byte represented by UC. You can see that, through these two moves that we're very simply taking the low order byte of the value and storing it into UC, consequently truncating the high order bits. So we'll go ahead and perform these operations. So we'll perform this operation and print out the value, and you can see that we do in fact end up with 44, which is the value that we predicted correctly that we were going to get. For signed to unsigned conversion, this is a little bit more complicated. Using signed integer types is always more complicated than using unsigned integer types. So positive values are preserved if they can be represented in the new unsigned type. Negative or overly large positive values that are outside the range of the resulting unsigned type are converted by repeatedly adding or subtracting one more than the maximum value that can be represented in the new type, which is also again 2 to the W, where W is the width of the new type, until the value is within the range of the new type. So in 2's complement representation, the bit pattern is preserved after either sign extension or truncation of the high order bytes, assuming the width is changed. So here's a chart that shows signed to unsigned conversions on x86-32 platform. So on the left we have some signed types that the conversion is coming from. So we have conversions from signed char, signed short, signed int, or signed long, which are both 32-bit signed values on this platform, and signed long. And we're going to convert these to unsigned char, unsigned short, unsigned int and long, which again are both 32-bit unsigned values, and unsigned long. So the boxes here that are marked in yellow are conversions for which the high order bit loses its function as a signed bit, meaning that the bit pattern is misinterpreted. When this happens, positive values are preserved, but negative values become large positive values because the signed bit is now interpreted as a part of the magnitude of the value. The boxes up here that are shown in this pinkish color mean that the high order bytes are truncated so that data is lost, meaning that only sufficiently small positive values will be preserved. So, for example, if we convert from signed char to unsigned char, there's the same number of bits in each representation, so the bit pattern is preserved, but the high order bit might lose its function as a signed bit. Same thing happens when we go from signed to any unsigned type. There's always the possibility, if this is a negative value, that it's going to be sign extended and the magnitude of the value is going to be lost. So for other types, such as, let's just take signed int for example, if we convert from signed int to unsigned char, this is going to be a 32-bit type and unsigned char is going to be an 8-bit type. So there's going to be a truncation and only the low order bytes are going to be preserved. So in this case, only sufficiently small positive values will be preserved. Everything else will be truncated, and the resulting sign, well, we're converting to an unsigned type, so we're always going to end up with an unsigned value. Now in the case where we're converting from signed int or signed long to unsigned int or unsigned long, the bit pattern will be preserved as is because these types, they are both 32 bits in length. But for larger types such as unsigned long, the bit pattern stored in signed int or signed long will be sign extended, and again there's the possibility of losing a value. If this is a negative value, we'll end up with a very large positive value. So finally, we're going to look at conversions to signed integer types. When a value with an arbitrary integer type is converted to a signed integer type, if the value can be represented in the new type, it's preserved. If the value cannot be represented in the new type, either the result is implementation defined or an implementation defined signal is raised. So this is quite different from conversions to unsigned types that are well defined by the C standard. Conversions of an arbitrary integer type to a signed integer type with a larger width is always safe. If an integer value cannot be represented in the new signed integer type, a common implementation defined behavior is to truncate the high order bytes if the width of the new type is smaller than the width of the original type and preserve the resulting bit pattern. Consequently, both the sign and the magnitude of the resulting value might change. So let's go to Visual Studio and see what we mean by this. So here we've got a very simple program that fits onto one page, and I'm going to go ahead and build this at warning level 3, which is the default warning level, and you'll see that this code builds cleanly. But if I go back and increase the warning level to warning level 4 and rebuild this program, you'll now see that we do get a diagnostic message, which is that there is a signed-unsigned mismatch in this equality comparison. So this is the type of warning message that a lot of programs will ignore, but probably shouldn't. But of course, you only have the opportunity to ignore this diagnostic if it's issued by the compiler, which it won't be in Visual Studio unless you set the warning level to 4, and other compilers may or may not provide a diagnostic for this line of code. So let's go ahead and start debugging. So if we look at this program, again, it's quite trivial. We're taking an unsigned integer type, UI, and we're assigning it the value uint_max, which is the maximum value that can be stored in a type of unsigned int. We're then declaring another variable signed char c and initializing it to -1. So -1, of course, is well within the range of assigned character type on this platform, which has a range of -128 to +127. Next, we're going to compare C to UI and print out the question, does -1 equal 4 billion something something, which seems improbable that these two values can be the same. So if we look carefully at the comparison, let's think about what's going on here. So first, let's take a look at C, and C is a signed char type. So because of the integer promotions, C is going to be promoted to a 32-bit signed value, to signed int type. So to promote C to a larger signed type, we're simply going to sign extend the value. And then we're going to compare this signed int with an unsigned int. So because of the usual arithmetic conversions, the signed int has to be converted to unsigned int. So again, we're comparing apples to apples. So now we're comparing the value c represented as an unsigned int to this value ui. So if I look at the assembly code here, you can see this is exactly what's happening. We're going to move the byte stored in C into the 32-bit EAX register, and because it's a signed char, it's a signed value, we're going to use the move SX command, which will sign extend the value as it moves it into the register. So let's go ahead and execute that statement. And next we're going to now compare the contents of the EAX register with the 32-bit value stored in UI, and what we're finding is that these two values, in fact, well, let me go back to the C, turn out to be the same. So in this next statement, we are in fact going to print out that -1 equals 4 billion something something, and you'll see that here in the output window. So again, the reason for this is that -1 is a signed char is represented by all bit set. So when we sign extend that to a 32-bit value, it's going to sign extend, and we're going to have 32 bits with all bits set. uint_max likewise is represented by all bits set. So because of the integer promotions and the usual arithmetic conversions that require the types to be compared as unsigned int, we're going to find that these two values turn out to be identical when compared in this context. So here's a table which shows conversion from unsigned to signed types on an x86 32 platform. So again, along the left we have the unsigned types we're converting from, and along the top we have the signed types that we're converting to. The boxes here that are shown in yellow mean that the high order bit is going to become the sign bit, meaning that the bit pattern might be misinterpreted, with large positive values becoming negative. And the pink boxes mean that the high order bytes might be truncated and data loss, meaning that only sufficiently small positive values are preserved. So let's go across this row of unsigned short because we get a little bit of everything. So if we convert from unsigned short to signed char, unsigned short is a 16-bit value on x86-32. Signed char is an 8-bit value. So this means the high order byte is going to be truncated. We're going to preserve the low order byte, and the resulting value may be positive or negative depending on what the high order bit in the resulting value is, whether it's set or cleared. When we convert from unsigned short to signed short, both of these types are 16 bits, so the value is going to be preserved. But the high order bit becomes a signed bit, meaning that if the high order bit was set in the initial value, we're going to end up with a negative value here. So conversions from unsigned short to signed int, signed long, and signed long are safe and are accomplished by 0 extending the unsigned value. So the reason these are safe are because the complete range of values that can be represented as unsigned short can also be represented as signed int and signed long, because there's sufficient precision here to represent the resulting value. So there's never, in this case, a loss of value. So in summary, implicit conversions do simplify the C programming language. Programmers are very used to performing operations on different types and having the conversions handled implicitly by the language. However, conversions do have the potential for lost or misinterpreted data. So it's important to avoid conversions that can result in a loss of value, meaning that the value is converted to a type where the magnitude of the value cannot be represented, or a loss of sign, meaning that it's a conversion from a signed type to an unsigned type where the sign cannot be preserved. So integer conversions to types with greater rank and the same signedness are guaranteed safe for all data values on all conforming implementations, but other conversions, again, are frequently at risk of either losing value or losing the sign, and so you have to be quite careful to avoid either of those conditions.
Integer types and integer conversions lay the groundwork for what we really want to do, which is to perform operations on integer values. Most integer operations have undefined behaviors. Some also have implementation-defined behaviors. Many of these behaviors are frequently surprising to programmers. In this lesson, you learn the behaviors of common integer operators, how to avoid undefined behaviors, and how to program safely and securely in the presence of implementation-defined behaviors. The specific operations we'll cover are assignment, addition and subtraction, multiplication and upcasting, division remainder, and shifting.
So we're going to now look at assignment. In simple assignment, the value of the right operand is converted to the type of the expression and replaces the value stored in the object designated by the left operand or L value. So assignment is really about moving data from one place to another, and that doesn't mean it's necessarily simple or error-free. So I have a fairly small program here that has a few components because we're going to step through this for different examples in this section. But let me go ahead and build this. And you'll see that this code is building cleanly. Now, this is being built at warning level 3, so I'm going to enable all warnings and go ahead and rebuild this. And we'll see when we rebuild this, we're now having a couple of warning messages generated, including one on this line that warns that there's a conversion from int to char and possible loss of data. So that's a useful warning, and it is pointing out a problem with this code. So once again, it is important to compile at high warning levels and to address all the diagnostics. Some of the problems in this program are not being diagnosed, so you can't depend upon diagnostics, but you want to take advantage of them when they're available. So let's go ahead and start debugging this code. And so we're at this initial conditional statement, and you see that we have a call to a function f. We're assigning the result of f to this character type variable c, and then we're going to compare the result to -1. So what I'm going to do is I'm going to step into this, and you'll see that the function f is really doing something quite simple. But let me single step, and I'll actually show you the assembly code here, just to show you that all it's doing is returning this value 255. So in order to do that, the function moves the value fox or 255 decimal into the 32-bit EAX register. So I'm going to go ahead and continue, and we'll go through a few instructions and then return to the calling routine. So f has now returned the value 255 in the EAX register. So what's going to happen now is we're going to implement this assignment statement. So we're going to take the low order 8 bits of the EAX register, represented by AL, and we're going to move that into the storage referenced by C. So we're just moving 8 bits of storage into this 8-bit char value. So the next step, and I'll go ahead and do that, the next step is we're going to move that value that we just stored in C back into the EAX register, except now we're going to use a move SX instruction. So we're going to move those 8 bits back in, but we're going to sign extend that into the high order 32 bits. So we'll go ahead and execute that instruction. And you'll see now that the EAX register, rather than just have the value FF, winds up having all bits set, or the value -1 if interpreted as a signed integer value. And the reason for this, of course, is because the high order bit in the low order byte was set, and so that signed value is extended through the high order bit so we can maintain the original value, presumably -1. So you can now tell that this comparison to all bit set is going to compare true. So we'll go back to the main body of the code. And yes, in fact, this turns out to be true. So again, what's happening here is that the int value returned by this function f is going to be truncated when it's stored into the storage allocated for C, which is only 8-bit char type. And then that value will be converted back to a 32-bit value because of integer promotions before comparing with -1. And as a result of that process, we wind up generating a value -1 on the left-hand side of this comparison. And so the result of this function, the value 255, turns out to be equal to -1 in this context. So you just saw an implementation where plain char is represented as signed char, or has the same range of values as signed char. In an implementation where plain char has the same range of values as unsigned char, and of course char is still narrower than an int, so for example char is an 8-bit value and int is a 32-bit value. The result of that conversion can never be negative, because of course an unsigned char can never have a negative value. So in that case, the operands will never compare equal. So that code will be wrong in that circumstance as well. So for correctness and for full portability, the variable C needs to be declared as an int. So we're going to continue on to the next function, g. And this function is quite simple. We're declaring 3 variables. One is a char variable c, another is an int variable I that I'm initializing to 255, and a long variable L that's uninitialized. And we have here kind of a nested assignment statement. So we have an assignment expression where we're going to assign the value stored in I, or 255, to C, and then the result of this assignment expression is going to be assigned to this variable L, which is a long type. So let's look at the assembly code for this. You can see we're initially moving the value I into the AL register, and so what's happening here is we're just taking the low order byte, which again has the value 255, and moving that into the AL register. Next, we're going to move the value of I that we stored in the AL register into the byte represented by C. So again, because the resulting type of this value is C, we're not getting a 32-bit value. We're actually truncating off the high order bytes. So next, we're going to take this value stored in C, and we're going to assign it to the storage referenced by L. So in this case, we'll move this value back into the ECX register using the move SX command. So this will cause these bits to be sign extended. So let's go back to the C code. So we're going to go ahead and perform those assignments and print L. And you can see here below that L has the value -1 because, again, this 255, when it's stored as a character type, the high order bit becomes a sign bit. And when it gets converted to long, that sign bit's going to be extended. So this is very similar to the previous example. And again, we start with a value that's stored in the int, and they can fully represent it as an int, and we're storing it eventually as a long, and of course this value can also be represented as a sign long, but we're winding up with an incorrect value because of this immediate store into a char type that causes this truncation to occur. So the first problem is the problem of misinterpreting values. So an assignment from an unsigned integer to a signed integer, or from a signed integer to an unsigned integer of equal width, is never going to result in a loss of data because you have enough bits to represent all the bits from the source, but it can result in the resulting value being misinterpreted. So in the following example, a negative sign value is going to be converted to an unsigned type of equal width. And I'm going to just say continue. And we're now in this function that is going to do a conversion from a signed int to an unsigned int. So we initially give the signed int the value -3, and now we're going to store it in SI into UI. Now, because the new type is unsigned, the standard requires that the value is converted by repeatedly adding or subtracting one more than the maximum value that can be represented in the new type, in this case being unsigned int, until that value is within range of the new type. So if we look at the assembly code here, you can see that really this is a very simple operation. So we're moving the 32 bits from SI into the EAX register, and then we're moving those 32 bits into UI. So there's not really any conversion or any modification of the data that's taking place here. But we now have a value that's an unsigned type, and if we access it as an unsigned type, you can see here below that it suddenly has the value of this very large value of 4,294,000,000, etc. So we'll go ahead and print that out, and I'll just show you the output window that in fact UI does have this very large value. The last problem is the problem of truncation. So truncation will occur as the result of an assignment or a cast from a type with greater width to a type with lesser width. And of course, data may be lost if the initial value cannot be represented in the resulting type. So for example, let's go back to hit continue. We're going to take two unsigned char values of 200 and of 90. So the range of unsigned char on this platform is 0 to 255. So both of these values can be represented. But of course, the sum of these two values, 290, is outside the range of the resulting type, which is also unsigned char. So let's go ahead and we can look at the assembly code for this. So we're going to move the byte stored in C1 into the EAX register, and we're going to 0 extend that value because it's an unsigned value. Okay, then we're going to move the byte represented by C2 into the ECX register, and again we'll 0 extend that because it's an unsigned value. We perform a 32-bit addition operation, and at this point we do have the correct result of 122 hex or 290 decimal, but now is where we get into trouble because we're going to only move the low order byte from the AL register, the low order 8 bits of the EAX register, back into the storage represented by sum. So now if we go back to our C code, you'll see that sum now has the value 34 and not the value 290 that we would normally expect to get from adding 200 to 90. But again, it's a result of truncation because the value 290 is outside the range of this unsigned char type. Addition can be used to add two arithmetic operands or a pointer and an integer. When you're adding a pointer and an integer, the result of that expression is a pointer. So that's covered under pointer arithmetic and not going to be discussed in this lecture, which is concerned with integer addition. So if both operands are of arithmetic type, the usual arithmetic conversions that we discussed in the conversions lecture are performed on each operand. Integer addition can result in a signed overflow or unsigned wraparound if the sum cannot be represented in the resulting type. The x86-32 instruction set includes an add instruction of the form add destination source, and it will add the destination operand to the source operand and store the result in the destination operand. The add instruction sets flags in the flags register. It will set an overflow flag indicating signed arithmetic overflow has occurred, or the carry flag to indicate unsigned arithmetic overflow or wrapping has occurred. So here's an illustration of the x86-32 flags register, and you can see that there's an overflow flag OF and a carry flag CF that will be set for the corresponding signed and unsigned overflows. So the overflow flag, again, denotes a signed arithmetic overflow and can be detected using either the jump on overflow instruction JO or the jump if not overflow instruction JNO. And these conditional jump instructions are placed immediately following the add instruction before some other instruction has the opportunity to set those flags or reset those flags. Unsigned wraparound detection is performed using the carry flag. Unsigned wrapping can be detected using the JC or jump if carry instruction or the JNC jump if not carry instruction. And again, these conditional jump instructions are placed immediately following the add instruction. x86 also includes a sub instruction that takes the form sub destination source, and this will subtract the source operand from the destination operand and store the result in the destination operand. The sub instruction also sets both the overflow flag to indicate signed arithmetic overflow and the carry flag to indicate unsigned arithmetic overflow. So there are actually no distinctions between signed and unsigned integer arithmetic when adding or subtracting or multiplying integer values in 2's complement representation. This means that the overflow and carry flags need to be interpreted in context of whether or not a signed or unsigned operation is being performed. So here we have a Visual Studio project. It's a very, very simple program where we declare two signed ints SI1 and SI2 and give them arbitrary values. And we also declare two unsigned ints UI1 and UI2 and give them arbitrary values. And we're simply going to perform signed and unsigned addition, print out the results, and then perform signed and unsigned subtraction, and then print out the results. So what's going to be most interesting about this is looking at the disassembly. Now, there's really no errors in this code. This is pretty simple code, but I'll clean and I'll build just to show that, yep, there's no errors. So let's go ahead and start debugging. I'm going to stop at this first addition, and as promised, we'll go straight to the disassembly. So you can see that we have an add here. Well, we're moving SI1 into the EAX register, and then we're adding SI2, and you can see that we're using an add instruction for this signed integer arithmetic. And right below, we're performing an identical set of instructions to add UI1 to UI2, and again, the same add instruction is used. So you can see in both cases that we're using the add instruction to add both signed and unsigned values. And you can also note that there are no jump instructions being inserted here to test the flags to determine if wrapping or overflow occurred. So the C language doesn't insert those instructions and doesn't test those results. So in the case of this implementation, they just wrap around silently. So if we scroll down here a bit, we have also the subtraction instructions, and you can see very similar behavior. The signed subtraction between SI1 and SI2 uses the sub instruction, and the same is true of the unsigned result, also uses subtraction, because again, there is no difference on 2's complement machines between signed and unsigned addition and subtraction. And once again, you can also see that there are no flags, there are no jump instructions being inserted here to test the overflow or carry flags in the flags register. The x86-32 instruction set includes a mul, unsigned multiply instruction, and imul, signed multiply instruction. The mul instruction performs unsigned multiplication of two operands and stores the result in the destination operand. The imul instruction does roughly the same thing, but performs signed multiplication of the two operands and then stores the result in the destination operand. The principal difference between the mul unsigned multiply instruction and the imul signed multiply instruction is in how they handle the flags. So for the mul instruction, the overflow and carry flags are set to 0 if the upper half of the result is 0, otherwise they're set to 1. For the imul instruction, the carry and overflow flags are set when the most significant bit, including the sign bit, are carried into the upper half of the result and cleared when the result, including the sign bit, fits exactly in the lower half of the result. So to determine the number of bits necessary to represent the product of two integers, we can look at the signedness of the type and the width n of the integer operands. So for unsigned values, which have a range of 0 to 2 to the n minus 1, the resulting product can be stored in 2n bits. The way we can determine that is we'll take the maximum value, which can be represented in one of these operands, which is 2 to the n minus 1, and square it. So this will give us the result 2 to the 2n minus 2n plus 1, which resolves to less than 2n bits. For signed 2's complement, we have to look at both the minimum possible value that can be produced from multiplying two signed integer operands and the maximum value. So the signed 2's complement range is negative 2 to the n minus 1 to 2 to the n minus 1 minus 1, because again, 2's complement is an asymmetrical representation, and there's one less value available to represent a positive number than a negative number. The minimum 2's complement product that can be produced can be calculated by multiplying negative 2 to the n minus 1, the minimum representable value, by 2 to the n minus 1, which is the maximum representable value. And that gives us the result, negative 2 to the 2n minus 2 plus 2 to the n minus 1. So here, the result can be stored in 2n minus 1 bits. For signed, the maximum value that can be produced by multiplying two signed numbers, we can multiply the min value, negative 2 to the n minus 1, by itself, or square it, and get the result 2 to the 2n minus 2. So this value requires up to 2n bits to represent, but only for the worst case scenario, which is squaring the minimum value. So let's look closely at the microcode for the mul instruction. We'll see here that we have a operand size of 8 bits, which is stored in source, and we're going to multiply it by an 8-bit value stored in the AL register, which is the low order byte of the 16-bit AX register. So here, we're taking the product of two 8-bit operands and storing it in a 16-bit destination register. So we've allocated twice as many bits for the result as the larger of the two operands, and that ensures that the result of this multiplication can always be represented. For 16-bit operands, we'll multiply the value stored in source by the value in the 16-bit AX register, and we'll store the result in the combination of the DX and AX registers, which gives us 32 bits to represent the result. For 32-bit operands, we'll multiply a 32-bit source by the EAX register, which can store a 32-bit value, and we'll store the result in the combination of the EDX and EAX registers, so we have 64 bits to represent the result. So one obvious question you might have is, for example, why don't we store the result of this 16-bit operation in the 32-bit EAX register? And the reason is just because of the history of this processor. At one point it was a 16-bit processor and there was no EAX register to store the result in. So it was necessary to use this combination of 16-bit registers, and that just carried forward. So multiplication is clearly prone to overflow because even multiplying relatively small operands can result in an overflow. One solution to this problem is to allocate twice the storage for the product of the larger of the two operands, and then check the resulting value to determine if overflow has occurred. For signed integers, an overflow would be indicated if there were a bit pattern other than all zeros or all ones in the upper half of the result, and the signed bit in the lower half of the result. If the upper half contains all zeros and all ones and the signed bit matches, that indicates that no overflow has occurred. For unsigned integers, it's considerably simpler to detect overflow. All you need to do is to see whether any bits in the upper half of the result have been set, and if so, that indicates overflow has occurred. I have a relatively simple program here that implements an alloc blocks function. The purpose of alloc blocks is to just check to see whether two values being multiplied are going to result in wraparound. If they do wraparound, we're going to return null and not allocate the storage. However, if the values are within the range of the type, then we're going to go ahead and multiply and allow that allocation to be performed. So I have three different versions of this function. The first is an incorrect version. The second is a correct but implementation specific version of the function, and the third version is a portable version. So we'll look at all three of these solutions. So first of all, let me go ahead and build this solution. You can see that this code builds cleanly at the highest warning levels, so there's no diagnostics being issued at all. And we'll go ahead and start debugging. And so you'll see that I'm passing this interesting value of uint max divided by 3 plus 100. So I just wanted to select a value here which would wrap around when multiplied by 3, which is what happens in the alloc blocks function. So let me go ahead and step into this, and you'll see that we're about to multiply this argument that's been passed by 3. And on this architecture, on a 32-bit architecture, size t is represented by a 32-bit unsigned value, and unsigned long is represented by a unsigned 64-bit value. So we're going to multiply this 32-bit value by another 32-bit value, 3, and store the result into alloc, which is a 64-bit value. So we'll then test alloc to see whether it's less than size max. So if it's less than size max, we can assume that no overflow or wraparound has occurred in this multiplication, and that we're free to go ahead and perform the allocation. If alloc is greater than size max, we can see that we've set some bits in the high order 32 bits of this 64-bit result. Consequently, wraparound has occurred, and we need to return null. So let's look at the disassembly. So the first thing that happens here is we're going to move C blocks into the EAX register. I'll go ahead and single step. And now we're going to multiply this constant 3 by the value of C blocks stored in the EAX register. But now we're doing something interesting, which is we're going to XOR ECX by ECX, producing a 0 in the ECX register. And then we're going to move EAX, the result of this multiplication, into the low order 32-bit alloc, But then we're going to move the 0 into the high order 32 bits of ALEC. So let's go back to the source code. So the problem here is that this multiplication is actually a 32-bit unsigned multiplication. So we're multiplying a 32-bit value by another 32-bit value, and this is going to produce a 32-bit result. And so it's quite possible, in fact, that this operation will wrap around. And because of that, ALEC can never, ever be larger than size max, even when this result wraps around. So that's why this solution is incorrect. It will never detect wraparound. So let's go ahead and step through this, and we'll go back to the main, and you'll see here that P in fact has a value. So the allocation was performed, and as promised, this incorrect version of ALEC blocks failed to detect wraparound. The problem here is that to be compliant with the C standard, multiplying two 32-bit numbers in this context is required to yield a 32-bit result. So the C Standards Committee did consider modifying the language, but the decision was made not to do so because it was felt it might be burdensome on architectures that do not have a widening multiplication instruction like the Intel processor does. So in fact, in this example we just looked at, we were producing a 64-bit result, but then we were discarding the high order 32 bits of that result, and as required by the standard, zeroing out the high order 32 bits. So the correct result can be achieved by casting one of the operands. So let's go back to Visual Studio, and I'll step into this corrected version of the ALEC blocks function. So now you can see that I'm casting the cblocks operand to the unsigned long type in order to force this multiplication into a 64-bit operation so that we do get a valid 64-bit result for ALEC. So let's look at the assembly here. You can see we're moving cblocks into the EAX register. We're then moving this constant 3 into the ECX register, and we're then going to multiply these two registers together. We're going to then store the low order 32 bits of the result into the low order 32 bits of ALEC, and then we're going to store the high order 32 bits of the result stored in the EDX register into the high order 32 bits of ALEC. So now if I go back to the C code and we step through this and return to the calling function, you can see now that P is actually null, and that modified test did in fact detect wraparound and consequently did not perform the allocation. Okay, so that works all good and fine, but let's look at a portable version of this. So I'm going to step into the third and final implementation of ALEC blocks. And the problem with this previous version of ALEC blocks is that it has a non-portable assumption, which is it's assuming that there's twice as many bits in unsigned long as there are in size T. Now that's true for x86 32-bit platform where size T is an unsigned 32-bit type and unsigned long is an unsigned 64-bit type. However, on the x86 64 platform, size T is now a 64-bit unsigned type, so it's the exact same size as unsigned long, and consequently there aren't twice as many bits to store the result. A portable solution is just to test whether cblocks is less than size max divided by 3, and provided that it is, we could go ahead and perform the allocation. If not, return null. So let's go ahead and step through this. So we'll just perform this test, return back to the main function, and you can see again that P is null. So this portable version of ALEC blocks was able to detect the wraparound. So it's not necessarily the case that one of these solutions is correct and one of these solutions is incorrect, provided that you're only running on a platform in which this assumption that unsigned long has twice as many bits as size T, this solution will work fine. However, if you do want a portable solution, it is possible to implement a correct and portable solution as well. So division and remainder operations in C and C++ are more interesting than they might at first appear. We'll just start by looking at what the standard has to say, which is that the result of the division operator is the quotient from the division of the first operand by the second. The result of the remainder operator is the remainder. So this remainder operator is commonly referred to also as the modulo operator, but in the context of this sentence, you can see that it's clearly defined to be a remainder operation. In both operations, if the value of the second operand is 0, the behavior is undefined. That's the well-known divide by 0 error, so we won't discuss that in any more detail. When integers are divided, the result of the division operator is the algebraic quotient with any fractional part discarded. So more precisely, if the quotient a divided by b is representable, the expression a divided by b times b plus the remainder when a is divided by b shall equal a. Otherwise, the behavior of both a divided by b and a remainder b is undefined. So, in other words, if the quotient is not representable, these operations produce undefined behaviors. So the x86-32 instruction set includes both a div and idiv instruction. The div instruction divides the unsigned integer value in the AX, DXAX, or EDX, EAX register by the source operand and stores the result in the AX, DXAX, or EDX, EAX registers. The idiv instruction performs the same operation only on signed values. Unlike addition, subtraction, and multiplication, the div instruction must be used for unsigned division and the idiv instruction used for signed division in order to get the correct results. So let's take a quick look at Visual Studio. And again, we have a very simple program here, and what I mainly want to do is just show you how the signed and unsigned division occurs on this platform. So let's go ahead and do clean followed by a build, and you can see that this was built cleanly. So we'll go ahead and start debugging, and again I want to go immediately to the disassembly. So we'll look initially at this signed integer division, and it starts by moving SI1 into the EAX register, followed by a CDQ instruction. So the CDQ instruction is going to take the signed bit from the EAX register and extend it into every bit in the EDX register. So this is a typical or normal sign extension of a 32-bit value into a 64-bit value, represented by the combination of the EDX and EAX registers. We're then going to perform an idiv instruction, and again we're using idiv because this is a signed division operation. If it were unsigned, we would need to use div. So we're going to divide the value stored in EDX and EAX with the divisor stored in SI2, and then we're going to move the quotient from EAX register into the S quotient signed integer value. So below we have an unsigned integer division, and this starts the same way, moving UI1 into the EAX register, but the next step is different. So in the signed operation, we performed a CDQ to perform a sign extension. Here we're doing an XOR of the EDX register by itself in order to create a 0 value in the EDX register. So this is for the purposes of 0 extending this 32-bit unsigned value into a 64-bit value. We then perform the division, and the division is performed using the div instruction as required for an unsigned division operation. And we'll then store the quotient from the EAX register into uQuotient. The x86-32 div and idiv instructions do not set the overflow or carry flags like the addition, subtraction, and multiplication instructions do. Instead, a division error is generated if the source operand divisor is 0, so the divide by 0 error, or the quotient is too large for the designated register, meaning that we had an integer overflow. A division error results in a fault on interrupt vector 0. So Programmers frequently incorrectly assume that division cannot result in overflow because the quotient must be smaller than divisor. However, there are a number of interesting corner cases where the quotient cannot be represented, resulting in undefined behavior. So for example, the value int min is divided by -1, or long min or long min is divided by -1. And of course the reason is that on a 2's complement representation, you're able to represent one more negative value than positive values. So when you try to change the sign on these minimum values by dividing by -1, you'll find that the resulting value cannot be represented. The other interesting problem is with remainder. So if we were to take int min, remainder -1, the mathematically correct result would be 0. So -1 goes into negative int min times with a remainder of 0. So the problem is that many hardware architectures will implement the remainder instruction as part of the division instruction, which we've already seen can overflow. So consequently, overflow can occur during a remainder operation when the dividend is equal to the minimum negative value for the signed integer type and the divisor is equal to -1, just like it does for division. So we have here a division, a signed division. We're going to set SI1 equal to int min, and then we're going to set SI2 equal to -1. So let me single step through that, and I'll show you here that we did pass in an argument of -1 for the second argument. So we now are lined up to do a division of int min by -1. So I'll go ahead and execute that instruction. And you'll see that we do generate a fault and wind up with an unhandled exception and an integer overflow error. So let's break, and I'm going to go back now to this code. Okay, so I've changed the division to a remainder operation. I'm going to go ahead and rebuild this solution, and then we're going to start debugging. And so you can see now that SI1 has the value of, oh, sorry. So SI1 now has the value int min, SI2 now has the value -1, and if I go ahead and single step, again you'll see the unhandled exception and the integer overflow, this time resulting from a remainder operator instead of a division operator. So the final integer operations we're going to look at are bitwise shifts. So these include left shifts of the form shift expression, left shift additive expression, and right shift, which is shift expression, right shift additive expression. Integer promotions are performed on each of the operands, each of which has an integer type. The type of the result is that of the promoted left-hand operand. So bitwise shifts for both left and right shift are undefined if the value of the right operand is negative or greater than or equal to the width of the promoted left operand. So in both cases, that's just weird things to do. So left shift, the result of E1 left shift at E2 is E1 left shift to E2 bit positions. That's a good example of something you can write, but you can't say without sounding dumb. The vacated bits are filled with zeros. So you'll see here, as bits are vacated to the left, we're going to backfill with zeros. If E1 has a signed type and a non-negative value, and E1 times 2 to the e to the 2 is representable in the resulting type, then that is the resulting value. Otherwise, the behavior is undefined. So, for example, if E1 has a signed type and a negative value, we have undefined behavior. If E1 has an unsigned type in the expression E1 left shifted E2 bits, the value of the result is E1 times 2 to the E2 power, reduced modulo 1 more than the maximum value representable in the resulting type. So C, of course, requires modulo behavior for unsigned integers. And this behavior is generally well understood, and expressions that invoke this behavior are generally fine. The one thing to remember, of course, is if you're trying to multiply some values together or divide some values, just multiply or divide. You shouldn't try to prematurely optimize by using left and right shift operations to perform division and multiplication. The compiler will do that for you when appropriate. So for right shifting, the result of E1 right shifted E2 bits is, of course, E1 right shifted E2 bit positions. If E1 has an unsigned type, or E1 has a signed type and a non-negative value, a 0 or positive value, the value of the result is the integral part of the quotient of E1 divided by E2. I think what I'm going to do here first is just show you some safe implementations of these functions. So for signed left shift, there's 3 different problems that you have to eliminate which can cause undefined behavior. So the first of these is that the left and right hand operands must be non-negative. The second problem is that we can't shift more bits than the number of bits available in the promoted left hand operand. So in this case, the promoted left hand operand is going to be an int, and so we need to multiply the size of an int by char bit, and the char bit macro defines the number of bits for the smallest object that is not a bit field. So basically the size of a byte on that implementation platform. So we have to just test and make sure that the number of bits we're trying to shift isn't greater than this value. The third requirement is that the result has to be representable. So what we can do is we can right shift int max by SI2 bits and make sure that value is less than SI1. If this is false, if SI1 is greater than int max right shift to SI2, that means the result cannot be represented, and again we have an error condition. So this signed left shift, there's always an interesting question of what to do with errors. Most of these shift operations are pretty innocuous when it comes to undefined behavior. So all we've done here is to print a standard error that there's been undefined behavior in the shift operation. You might want to do something more drastic. You might want to have an assertion or something like that to detect these at runtime, but most likely you're not going to want to have the code fail because of this, because again it usually does have a pretty well defined behavior and fairly innocuous behavior on most platforms. So for signed right shift, there's fewer requirements, simply that the right operand has to be again non-negative, and also that the number of bits being shifted isn't greater than the size of the promoted left-hand operand. For unsigned shift, right shift, the only requirement is that we're not shifting more bits than exist in the promoted left-hand operand. And for unsigned left shift, it's the same. Signed right shift has some interesting implementation defined behavior. So if E1 has a signed type and a negative value, the resulting value is implementation defined, and it can be either an arithmetic sign shift or logical unsigned shift. The arithmetic sign shift pays attention to what the sign bit is and makes sure that sign bit is propagated. So if the sign bit is a 1, that 1 will be propagated into each bit position that's vacated. If the sign bit is a 0, that 0 will be propagated into each vacated position. For logical unsigned shift, this is kind of a dumber operation. It's going to ignore the sign bit and just shift in zeros. So the C89 committee affirmed the freedom in implementation granted by KNRC in not requiring signed right shift operations to sign extend, since such requirement might slow down code, and because the usefulness of signed extended shifts is marginal, meaning that it cannot always be used to perform a correct division operation. So the best solution really is to just simply avoid performing bitwise shift operations on signed values. Because the behavior is more prone to error, there's more cases for undefined behavior, And it's an unnecessary thing to do in most cases. If you're multiplying or dividing signed numbers, you should multiply or divide. If you're shifting, you're bit twiddling. And if you're bit twiddling, you should be bit twiddling on unsigned integers, because those are best used to represent bit fields. The Cert C Secure Coding Standard Guideline, Int 13C, use bitwise operators only on unsigned operands, recommends this practice and also recommends it for other bitwise operators. So for example, if you have an implementation in which right shift is arithmetic, the signed bit can be propagated. So let's look at what we mean in Visual Studio example. So here's again the same program we had earlier. I'll do a clean solution followed by a build. And you can see here that Microsoft Visual Studio is upset about our use of the sprintf function because it can be unsafe. And that's generally good advice. And we'll talk more about that in the strings lectures. But for now, we'll just go ahead and proceed. There's no diagnostics being issued on any of the shifts that we're performing. So I'm going to go ahead and start debugging. And we're already to this line, but let me show you what's going on. So we have a integer value stringify, which has the value int min. So this could really have anything, but I've selected a value here that's going to set the sign bit. And we have a buffer here consisting of 4 bytes. And so we've declared it in this sort of cutesy way of saying the size of this string literal, which including the no termination character is 4 bytes in length. And the reason we define that in a cutesy way is that we're planning on taking a integer value that's stored in stringify, and we're going to right shift it 24 bits. So we know we'll end up with a value that's represented in 8 bits, and then theoretically between the value of 0 and 256. So we're going to go ahead and, well, we've already calculated this stringify right shift at 24 bits and stored the result in shift. Now, the surprising thing is we were kind of thinking a second ago we're going to have a value between 0 and 256. But what we ended up here for shift is actually the value minus 128. So if we look at that in hex, you can see more clearly what the problem is here. And the problem is, because the original value we were shifting, which was 8 followed by zeros, because the sign bit was set, when we right shift it on this particular platform, which happens to have an arithmetic shift, the sign bit is filled in. And so rather than having a small value that fits neatly into 4 bytes, we're going to end up with a very large integer value here, which isn't going to fit. So let me take a look at this buffer, and I'm going to copy this and look at the memory at this location. So you'll see right now it's just some junk in here, but this is the location of buff, and there's 4 bytes that have been allocated for this particular character array. So we're going to go ahead and execute this sprintf instruction, and you'll see what happens is we're actually copying this very long string into this buffer. So we've exceeded the size of the buffer by a significant number of bytes. And so this is all writing outside the bounds of the array, or in software security terms, this is a buffer overflow. And of course, this can frequently lead to vulnerable code and erroneous code and all sorts of problems. So let's keep going. And what I want to do this time is go into this signed right shift function that we wrote, which is theoretically safe. So we'll go in here, and we're passing the same arguments as we saw in the previous example. So we check to see that SI2 is less than 0. If it is, it's an error condition. It has the value 18, so we're fine. 18 hex. And then we'll make sure we're not shifting more bits than the size of the promoted left-hand operand. We're not, so there is no error in this case. So we're going to go ahead and perform the shift and return the shifted value. So when we come back to the main, you'll see here that shift still has this same value. So this safe signed right shift function has not eliminated the error. And the reason, of course, is the behavior we're seeing is not undefined behavior, it's implementation defined behavior, and it's perfectly correct for this platform. So, part of the real risk here is that someone writes this code on a platform for which the implementation defined behavior of right shift is a logical shift. And then in that case, for that platform, this logic is perfectly fine. But then it's ported to a platform where the right shift behavior is arithmetic right shift, and suddenly we have a buffer overflow and it goes undetected. So let me show you next the use of unsigned right shift. So here we're going to pass the same arguments as we did in the previous example, except we're going to call the unsigned right shift. So these are signed values, of course, but we've already talked about conversions and implicit conversions, and these ints will just be implicitly converted to unsigned types. And that's okay if we know it's happening and we know what we're doing, which I'm kind of hoping we do. So we'll go ahead and step into that. We'll check for undefined behavior. There's no undefined behavior, so we'll go ahead and perform the right shift. And you'll see now that uShift has the value 80, which, let's go back here, and let's look at this again in decimal. So it has the value 128. So now, when we convert this to a string, this can be easily represented as an ASCII string in the number of bytes we've allocated. So this use of the unsigned right shift actually has solved the problem, which again is really one of the reasons we recommend the use of unsigned integers when performing these bitwise operations. It's a little bit too dangerous, it's too much undefined and implementation defined behavior when left shifting and right shifting signed values. So in summary, there are a number of operations in the C programming language, many of which are prone to various exceptional conditions. So for example, we looked at addition, which is subject to signed overflow and unsigned wrapping, and as well as subtraction, which is also prone to signed overflow and unsigned wrapping. Multiplication, which is particularly prone to overflow and wrapping because even small operands can fairly easily result in the results not being representable in the number of bits. Division, which is prone to signed overflow but not to wrapping because of the properties of 2's complement representation. And similarly, remainder, which is also prone to overflow and not wrapping. And we also looked at assignment, which is prone to truncation, but not subject to overflow or wrapping because this mostly just involves the moving of bits. So you'll see there's a number of other operations, and you have to be careful with most of these. There are some for which there aren't exceptional conditions, but you do need to understand the properties of each operation and how they can fail, and take precautions to carefully write your code to be correct for all possible operand values.
By now, you have learned about integer types from earlier lessons, including an introduction to character types and their representation and use as integer types in C language programming. In this lesson, you learn about how strings are represented as no-terminated character arrays in the C programming language. You learn about properties of arrays, as understanding their behavior is critical to understanding C language strings. You also learn about string literals and their use and idiosyncrasies in initializing arrays. You also learn about the underlying and undocumented philosophy behind the use of the character types in the C language.
So a string consists of a contiguous sequence of characters terminated by and including the first no character. The pointer to a string simply points to the initial character in the string, and the length is the number of bytes preceding the no character. So you see here we have a representation of a string in the C language. It's actually an array of characters, and you can see the pointer points to the first character, which is the H, and the length is the number of characters before the terminating no character, which also has to fit into the array. So because strings are implemented as arrays of characters, they are susceptible to the same problems as arrays. So one of the problems with arrays is really figuring out how large they are, figuring out how many number of elements in the array. The strLength function can be used to determine the length of a properly no-terminate string, but not the size or space available in the array. Again, we have a really simple program. I'll go ahead and clean this and do another build, so you can see that it does build cleanly without any sort of diagnostics at all, and we'll start to debug it right from the beginning. So we're assigning a string literal to this character array we've declared, and let's go ahead and do that. So this will initialize stir to this value and allocate sufficient storage for the string and the terminating null character. So now we're going to calculate the number of elements in the array. And we do that using a very standard idiom, which is that we take the size of the array and divide it by the size of each element in the array. So in the case of a character string, the size of each element is going to be 1, but it's okay to put this here anyway. The compiler will take care of optimizing it out if it's not necessary, and this same idiom will work for wide strings as well. So we'll go ahead and single step, and you'll see now that the number of elements in stir is 28, which seems to be about right. We'll go ahead and print that out anyway, and you'll notice because we're using Visual Studio that we're using the capital I conversion specifier because Visual Studio isn't entirely C conforming. Really, this should be %Z conversion specifier for use with size T type. So go ahead and we'll enter func and pass this stir that we just took the size of, and we just discovered that the number of elements in that array was 28. And we have the same string being passed here to func, so we'll recalculate the size inside this func, and you'll see exactly as expected that the number of elements is now 4. So clearly this can come as somewhat of a surprise, but what's happening here is something known as array decay. So when we pass an array to a function, it actually decays to a pointer to the first element of the array. And so we've made that even more confusing by using the array notation here, which is perfectly correct, but makes it appear as though we are passing an entire array, when actually what we're passing is a pointer to the first character of the array. So this notation is usually more understandable. People will more quickly realize that what's actually being passed here is a pointer to a character and not a complete array. So what happened in this calculation of the number of elements is we took the size of S, which now is a pointer, and because we're compiling this for a 32-bit model, so you wind up with a value of 4 for the size of the pointer divided by the size of each character, which is 1. So that can be surprising. It can lead to failure to allocate sufficient storage and all sorts of nasty problems like buffer overflows and so forth that can occur from there. In addition to narrow string, C programming language also supports wide strings. So wide strings are used to process the characters of a large character set, in which case each character may not be representable as a thin or narrow character, so instead they're represented as a wide character or WCHAR-T. And this generally takes up more space than an ordinary character. So most implementations we use either 16 or 32 bits to represent a wide character. Other than that, a wide string is very similar to a narrow string in C. It's a contiguous sequence of wide characters terminate by and including the first no wide character. The pointer to the wide string points to the initial wide character. The length is the number of wide characters preceding the no wide character. And the value is the sequence of code values that contain wide characters in order. So there are 3 concepts that get very easily confused but it's a very good idea to keep these concepts separate and to use differently named variables and arguments when referring to these very different concepts. So the three concepts are length, size, and count. Length is a property only of strings, and we've looked at it already. It's the number of characters preceding the no character or the no wide character in a wide string. The other two concepts apply only to arrays, but of course strings and wide strings are implemented as arrays in C. So the size of an array is the number of bytes allocated to the array, so it's the amount of storage. And the count of an array is the number of elements in the array. So what's a bit confusing is that for narrow strings, where each character is 1 byte, the size always equals the count. But this is not the case for wide string, where the size of the array, the number of bytes, is equal to the count, the number of elements, times the size of each element, or the size of W char T. A character string literal is a sequence of 0 or more characters enclosed in a double quote, as in XYZ. A wide string literal is the same, except it's prefixed by the letter L, as in LXYZ. So the type of a string literal in C is an array of char. Consequently, a string literal is modifiable, although modifying such an array is undefined behavior. Array variables are often initialized using a string literal and declared with an explicit bound that matches the number of characters in the string literal. So for example, we have a declaration of S which consists of 3 const char characters, and we're initializing it to the string literal ABC. So in this case, the size of the array is 3, but the size of the string literal, including the terminating no character, is actually 4. Consequently, the trailing no byte is omitted when copied into S. So, on the other hand, if you do not specify the bound of the string, the compiler will automatically allocate sufficient storage. So now we're just declaring const char S, and we're not specifying a bound, and initializing it again to the string literal ABC. In this case, S will actually be 4 bytes long, and will be initialized to the characters ABC and the terminating no byte character. So this approach simplifies maintenance because the size of the array can always be derived even if the size of the string literal changes. If you really want to declare a character array and not a string, meaning that you want just a sequence of characters without a terminating no character, the preferred way to do that is to just specify each of the 3 character literals. So in this case, we'll say character array S, and we'll give a bound of 3, and then we'll specify a comma-separated list of character literals to appear in each of the element positions of the array. If the character array has to be larger than the string literal it's initialized with, you can, in this case, specify an array bound. So here, we're declaring a character array S with a bound of 10, and we're initializing it to ABC. So in this case, there's sufficient storage for all 3 of these characters to be copied, including the terminating no byte character. So this will be a actually properly no terminated string. And now we can copy into the string using the strcpy function, and we'll copy in DEF. So at the end of this operation, we'll now have a character array which consists of the characters A, B, C, D, E, F, followed by a no character, and that will fit comfortably in the 10 bytes that we've allocated with some storage left over. So there are 3 character types in C language: char, signed char, and unsigned char. And those 3 types are collectively referred to as the character types. Compilers have the latitude to define char to have the same range, representation, and behavior as either signed char or unsigned char. So irrespective of which choice is made, char is considered a distinct type. The C standard also has a consistent philosophy for choosing character types. Unfortunately, it doesn't tell you what that philosophy is. The philosophy is that signed char and unsigned char are really only suitable for small integer values. So signed char, for example, can be used to represent small integer values in the range of -127 to +127, and unsigned char can be used to represent small unsigned integers in the range of 0 to 255. Plain char is the type of each element of a string literal, and it is really intended to be used for character data, where the signedness of the type has little meaning, as opposed to integer data where the signedness is important. The int type is also used to represent characters in C. So int is used for data that could be either EOF, which is a negative value, or character data interpreted as an unsigned char and then convert it to int. So for example, an EOF might be represented by -1 or all bits set, but a character type such as FF, if this were treated as a sign char and then converted to int, it would sign extend and you would end up with all bits set, which would be indistinguishable from EOF. However, if you treat this FF character as an unsigned char and convert it to int, it will need to zero extend. So what you'll end up with is all zeros in the high order 3 bytes followed by any sequence of bits set in the low order byte to represent the character. Or you'll end up with all bits set, which is the EOF character. Any other combination of bits is going to produce undefined behavior. So because int is used for data that could be either character or EOF, it's returned by the fgetC function, the getC function, getChar, and ungetC. And it's also accepted by character handling functions defined in the C type header because they might be passed the return value from a call to, for example, fgetC. The type of a character constant in C is also an int. It's the value of a plain char converted to an int. So this was changed in C++, and this can cause various problems because it's relatively easy to create a value that when passed to a character handling function, for example, will result in undefined behavior. Characters can also be represented at times as unsigned char. For example, unsigned char is used internally within the C standard library for string comparison functions, even though those functions operate on character data. So this ensures that the string comparison does not depend on whether plain char is signed or not. Unsigned char is also the only type that is guaranteed to allow access to all the underlying bits in the object. So the unsigned char type is used for situations where the object being manipulated might be of any type and it's necessary to access all the bits, such as with the fwrite function. So the CertC Secure Coding Standard recommends using plain char for characters in the basic character set for compatibility with the standard string handling functions. In most cases, the only portable operators on plain char types are assignment and equality operators, so you can perform an assignment, you could test for equality or inequality. One exception is the translation to and from digits. So for example, if char C is a digit, you can write the expression C minus the character literal 0 to produce a value between 0 and 9. So I've got a very simple program here, and the purpose of this program is mainly to show why you should represent strings as arrays of character of plain char. So we have size t len, and then we declare 3 strings. The first is a plain char string, cstir. The next is a signed char string called scstir for signed character string. And finally an unsigned character string called ucstir. And the program simply takes the length of each of these strings. So we have the length of the plain character string, the signed character string and the length of the unsigned character string. And I've set this to have the strictest enable all warnings, and I'll go ahead and build this solution. So you'll see that we do get an error here, a warning, that the function const char star differs in direction to slightly different base types from unsigned char. So that warning is generated for this line where we're taking the length of an unsigned character string. And the reason for this is that by default on Visual Studio, plain char is implementation defined to be a signed character string. So suddenly we're trying to pass an unsigned character string to str length, and that causes a incompatibility in type. Now what we can do is we'll go into the properties, and on the command line tab we'll add an extra argument, which is the J argument. So the J argument is going to declare by default that plain char should actually be represented as unsigned char. So we're going to change the implementation defined semantics for char. And now we'll go ahead and rebuild the solution. And you'll see again that now we've generated another error, but now it's on this line where we're taking the length of the signed character string. So now the problem is char is implementation defined to be an unsigned char. So suddenly there's an incompatibility on this line. So you'll see in any case, the only line which is never flagged as incorrect is when we take the length of the plain char string. So this is the correct and portable solution. So as we've seen, when you compile at high warning levels, which again is always a good idea, we're going to get warnings when converting from unsigned char to const char star when char is signed, and from signed char to const char star when char is unsigned. To eliminate these warnings, we would have to use cast, but the excessive use of cast really can make the code very difficult to read, and it can also hide legitimate warning messages that we want to know about. Furthermore, if we were to take this code and compile it with a C++ compiler, C++ tends to be fussier about types than C. The conversion from unsigned char to const char star and from signed char to const char star would wind up being flagged as errors requiring cast. So that code wouldn't even compile in that case. The C standard has a philosophy for using character types, and you should follow the same philosophy assumed by the standard. That includes using plain, unadorned char to represent ordinary character data, such as ASCII data, using int for data that could be either a character or an EOF, and using the wchar_t type to represent wide character data. And remember, the size of wchar_t is implementation defined, so don't assume that it's either 2 or 4 bytes. It could be either. You also want to be very careful when you're operating on values to know if that value represents a length, size, or count, or number of elements. And try to use appropriately named identifiers for these values so it's very clear to you later on and to others looking at your code what these values represent. Making mistakes, confusing these can lead to buffer overflows and other coding errors. The third piece of advice from this lesson is not to specify the bound of an array when initializing to a string literal. This avoids errors and simplifies maintenance. The compiler will do all the work of allocating sufficient storage for the entire string literal, including the terminating no character.
There are several different collections of APIs for managing C language strings, including the standard C string handling functions defined in string.h, the various POSIX APIs, and the bounds checking interfaces defined in Annex K of the new C11 standard. Each of these APIs has different characteristics in terms of their safety, security, performance, and portability. It is beneficial to decide on a consistent approach to handling character strings that best meets the requirements of the project. Otherwise, the decision is left to individual programmers who are likely to make different, inconsistent choices. The best way to categorize and understand these approaches is based upon the memory model assumed by the API. In this lesson, you learn about the memory models available to C language programming, as well as the advantages of bounds checking interfaces over the standard C string handling functions defined in string.h. More specifically, this lesson covers caller allocates, caller frees, bounds checking interfaces, callee allocates, caller frees.
So the first model for implementing string handling is when the caller both allocates and frees the storage. So this allows storage to be either statically or dynamically allocated before invoking the string handling functions, which makes the model optimally efficient by putting all the work in the hands of the programmer. So it also makes it clear when memory needs to be freed and is consequently more likely to prevent leaks. This model is implemented by the standard C string handling functions defined in string.h, the OpenBSD functions stir-lcopy and stir-lcat, and also the C11 Annex K bounds checking interfaces. So we'll look at each of these implementations in this lesson. So the first thing we'll look at is input using C99 interfaces such as getS. So the getS function is a known dangerous function and it has been deprecated in the C99 Technical Cardendum 3 and eliminated from the C11 standard, but we're just going to look at it as an example here anyway. I've got a small program here again, and we're going to build the solution. And you'll see in this case we get a massive number of warning messages. This first one is just unreferenced parameter, but the majority of these are warnings that I'm using these unsafe functions, and so I am. So let's go now to the program, and we'll just start by debugging. And I've set a breakpoint at the beginning at the invocation of this function to get yes or no. So we'll step into this function, and we've got a character array declared of 8 characters, and that's on the stack. So we're going to print a request for the user to enter a yes or no, and then we're going to call getS to get the response. And the problem with this, of course, is what happens if the user doesn't type yes or no, but instead types some really long input that is not expected by the program. So we check to see whether the response is no, and it's not because it's some really long input that's not expected by the program. And now we'll return back to main, and you'll see that we have a runtime error because the stack has been corrupted. And that's because this really long input has overwritten the stack. And that's really the basis for buffer overflow exploits and arbitrary code execution. So generally speaking, not a good thing. So again, the getS has been deprecated from C99 and eliminated from C11, and it's the one function in C languages that is never safe to use. And the problem with getS is it just doesn't specify any way of indicating how many characters are in the destination buffer. So it doesn't have any way to specify a limit on the number of characters to be read. So as you can see, it's just going to get a character, and it's going to keep reading characters in until either an EOF or end of line is found, but unfortunately it won't stop reading because the target buffer that's being writ is full. So the other major problem with the standard C string handling functions is that it's quite easy to make errors when copying concatenating strings because these functions do not know the size of the destination buffer. So here's a very simple example where we have a static array called name of 2048 characters. And normally you would think that would be sufficient for most inputs, but unfortunately users or attackers could type in very large strings. And so we are copying argv1, we're copying the static string equals, then we're copying argv2 into this character array, and any of these lines can overflow this buffer and result in a buffer overflow. So not all uses of strcpy are flawed. So for example, it may be possible to dynamically allocate the required space. So here we're figuring out what is the length of the source string. We're adding a byte to that to account for the terminating no byte character, and then we're dynamically allocating the storage. So that storage is successfully allocated. We can now safely copy from the source to the destination because we know we've allocated sufficient storage to make a copy of this string. So another problem with these functions is the failure to properly no terminate the strings. We're going to go back again to Visual Studio and see what we mean. So I'm going to start debugging again, and we'll just continue from here. Now I'll just simply say yes, that I would like to continue. And now we're going to enter this second copy function. So let me go into this copy function. And you'll see that we've got a few character arrays here, A, B, and C, of 16, 16, and 24 characters. And we're going to start copying into these, and we're going to use the strncopy function, which is going to limit the number of characters written. So we'll go ahead and copy this string literal into A, and let me look at my automatic variables here. So you'll see that A, B, and C have these random characters in them right now. So we'll do the strncopy, and we'll fill this buffer up. And you can see that this buffer, of course, goes from 0 to 15, and the 15th element contains the character F, which of course means that there's no space in this buffer for the terminating no byte character, so this array is not properly no terminated. If we continue and we do the copy into B, you'll see B again has exactly the same problem. It's not properly no terminated either. And so now we're going to do a strcpy from A to C, and when we do this, you can see that the strcopy is not creating a properly no terminate string. Instead, it's copying garbage that's in memory into the string. So the problem is these arrays might be right up against each other, or there might be some other data structures put between them. There might be padding, for example, to align these. So it's very much undefined behavior what happens when you start reading or writing memory outside the bounds of these arrays, as we do in this call to strcpy, because we didn't understand that these arrays were not being properly no terminated. Now, the reason for this is that the strncopy function, again, takes a destination array S1, a source array S2, and a size, and it will not copy more than n characters from the source to the destination array. But if there are no characters in the first n characters of the source array, the resulting array will not be no terminated. And this is the definition from the standard. So any conforming implementation of strncopy has to behave in exactly this manner. So strncopy is a fairly problematic function and really shouldn't be viewed as a replacement function for strcopy. So the problem here is that functions that restrict the number of bytes are frequently recommended to mitigate against these buffer overflow sort of problems, such as using strncopy instead of strcopy, fgets instead of gets, and snprintf instead of sprintf. But the strings that exceed the specified limits are truncated, resulting in a loss of data. So what you're being asked to do in these cases is to trade one problem for another problem, and that's not really an adequate solution. Why not just solve the problem instead? So OpenBSD developed some functions to try to address some of the weaknesses with the standard string handling functions, strlcopy and strlcat. So these were meant to copy and concatenate strings in a less error-prone manner. And so they take a destination, source array, and a size, just like strncopy does. Except strlcopy will copy the no terminated string from source to destination up to size characters, and strlcat will append the no terminate string source to the end of destination, and again, no more than size characters will be allowed in the destination array. So to help prevent against buffer overflows. Both these functions accept the size of the destination string as an argument. For statically allocated destination buffers, that's easily computed using the size of operator at compile time. For dynamic buffers, the size is not as easily computed, which means that, but at some point you passed a value to a dynamic allocation function to perform that allocation, and you just need to preserve that value as the size of that storage. So both of these functions, unlike stir and copy, guarantee the destination string is no terminated for all non-zero length buffers. So this is immediately an advantage over using stir and copy. So the stir lcopy and stir lcat functions return the length of the string they tried to create. For stir lcopy, that's simply the length of the source string. For stir lcat, it's the length of the destination before concatenation plus the length of the source. So to check for truncation, programmers need to verify that the return value is less than the size argument. And if the resulting string is truncated, the programmer now knows the number of bytes needed to store the entire string and can reallocate and recopy. So there's a solution for string truncation. The problem is that the solution is fairly complex, and most developers don't implement this solution, with the consequence that this function again is quite prone to string truncation because the interface is just too complex. So stir lcopy and stir lcat are available for several Unix variants, including OpenBSD and Solaris, but it's not available for GNU Linux, so it's not a widely available function, unfortunately. Now, the incorrect use of these functions can still result in buffer overflows. For example, if the buffer size specified is longer than the actual buffer length. And as mentioned, truncation errors are possible and almost likely if programmers fail to verify the results of the functions, which is not uncommon. So the bounds checking interfaces are alternative library functions that promote safer, more secure programming. For example, C11 Annex K defines functions such as strcpy _s, strcat _s, strncopy _s, and strncat _s, which are meant as safer replacement functions for strcopy, strcat, strncopy, and strncat, respectively. C11 Annex K also defines a getS _s function as replacement for getS and a variety of other functions as well. The alternative functions verify that output buffers are of sufficient size for the intended result and will return a failure indicator if they are not. This prevents data from being written past the end of an array, and also the strings are guaranteed to be no terminated. The C11 Annex K functions have an interesting history. They were initially developed by Microsoft to retrofit its existing legacy code base in response to a number of well-publicized security incidents. Those functions were subsequently proposed to the WG14 C Standardization Committee for standardization, and WG14 first published these as ISO IEC TR 24731-1, and then they were later incorporated into the C11 standard in the form of a set of optional extensions specified in normative Annex K. Interestingly, the current Microsoft implementation is actually non-conforming to the standard, and that's because the APIs underwent some evolution during the standardization process. They went through some changes, and Microsoft has not yet gone back and retrofitted their APIs to conform to the standard. So we'll look at an example of using the getS _s function to read in input from standard in. Unlike the getS function, getS _s will make it a runtime constraint violation if the input line is going to overflow the buffer being used to store it. So let's take a look at Visual Studio. And we've got a simple program here. I'll do a clean and a build. So this program is similar to the program from the previous example that used getS. So you'll see that we still have a warning about this unreferenced formal parameter that we're going to live with for now. And all the other warnings concerning the use of insecure functions, deprecated functions are gone because we've replaced those with the use of the _s functions. So let's go ahead and start debugging. And I have a breakpoint set again before the invocation of the getWireNo function. So we'll step into that function, and we're now going to first of all figure out what the size of the buffer is that we're going to store the response from the user into. We'll print the line asking the user if they want to continue or not, and then we'll go to get the response, this time using the getS_s function. And it takes two arguments, the buffer to store the response and also now the length, which is set to the size of the response. So this function, it no longer has undefined behavior like the getS function had, but it has now instead implementation defined behavior, meaning that if an overly long input is entered, it may or may not invoke a runtime constraint function, and what that function does is implementation defined. So let's go ahead and call the getS_s call to input a value which still may be longer than the buffer that has been allocated to store the result, but we'll hit enter anyway and see what happens. So we got a runtime error that was detected by this function, and it looks an awful lot like the last one, but you actually will get now a specific message that's being created by the runtime. So instead of getting this undefined behavior where it could result in an exploitable vulnerability, instead we're going to have a nice implementation defined diagnostic message being issued. So what happens with these _s functions, these Annex K functions, bounds checked interfaces, is that they will call a special runtime constraint handler function upon detecting an error. And that function might print an error message and or abort the program, or it could in fact just ignore the error completely and return. The behavior is up to the application programmer. So the programmer can control which handler function is via call to the setConstraintHandler _s function. Now, if this handler just simply returns, which is an option, the function that invoked the handler will need to indicate a failure to its caller using a return value. Consequently, programs have to check the return value of each call to any of the bounds checked functions and handle the errors appropriately for this case where the constraint handler is simply going to return. So we're going to go back to the previous example and remove the implementation defined behavior by adding some additional code. So let's go again to Visual Studio, and you'll see now that I have some code here that's been conditionally unincluded from the compilation. And there's two sets here. So down below is the standard way to set a runtime constraint handler that's going to simply ignore the error and return. However, I mentioned that the Microsoft Visual Studio implementation is non-conforming. So this code actually doesn't work, so I can't demonstrate it here. But instead, what we'll do is we'll show the original mechanism, which is still supported in Microsoft Visual Studio, of calling the setInvalidParameter handler. And this performs exactly or roughly the same capability, except the API for the parameter handler is different than the runtime constraint handler, and of course the name of the function is different. So we'll demonstrate this. So we'll go ahead and build this solution, and you'll see that there's a massive number of compilation errors because obviously I had my declarations in the wrong order. Rather still annoying feature of Microsoft Visual Studio. So we'll build the code with the declarations in the right order, and now everything is hunky-dory. We just have the one unreferenced formal parameter that we've grown accustomed to seeing and are quite comfortable with. So let's go ahead and debug the program again, and we'll jump into this getYesOrNo function, and we'll come down again to the getS call, and I will go ahead and type some really long input once again to make good and sure that we overflow the buffer. And what's happened now is that the bounds were definitely exceeded once again because we have just this very short length of len, but we did something different, which we printed out this message. So the reason we got this message and not the other behavior was because back here in main, again, we set this invalid parameter handler to my invalid parameter handler. And that handler is defined at the beginning of this function, and it takes a standard collection of arguments, one of which I'm not using, and it prints out invalid parameter detected in function, and in this particular file, and at the particular line, and with this particular expression. So now, that is the behavior that we see, and it's now well-defined behavior because it would behave the same way on any implementation that supported this interface, which unfortunately is only Microsoft Visual Studio because we're using the non-standard interface and not the standard interface. So, you know, there's still some bugs to work out, but it's an interesting improvement upon previous practice. So a couple other things I'll point out again about the runtime constraint handlers is that we set the runtime constraint handler in main in order to implement a consistent error handling policy throughout the application. So in general, you want to avoid setting specific constraint handler policies in library functions because that might conflict with the overall policy that's being enforced by the application. Meaning that library functions have to be written to assume that the runtime constraint handler is simply going to ignore the error and return. So it's necessary for these library functions to check the return status from these Annex K functions appropriately. So unlike the fgetS function, getS_s has a one-to-one relationship between input lines, meaning that because the getS calls would consume an entire input line, and getS_s is meant to be a very close replacement for the getS function, you also want getS_s to consume an entire input line. fgetS behaves differently. It's going to input a certain number of characters. So the fgetS function does allow properly written programs to safely process input lines too long to store in a result array. In general, it requires that callers of this function pay attention to the presence or absence of a new line character in the result array. So the C standard recommends using fgetS along with this additional processing based on the fact that fgetS will read in new line characters and store them in the array instead of using getS_s. This is up to you, but this is the recommendation from the C standard, and fgetS, of course, is widely available as a long-time standard C function. So we'll go back now and we'll look at the copy functions in C11 Annex K. So we have a strcopy_s function that, very similar to strcopy, copies characters from a source string to a destination character array up into and including the terminating no character. So it has the following signature, which is consistent with other _s functions. It returns an error as an error no t, and it takes an additional argument, which is an rsize t value, which specifies the maximum length of the destination buffer as S1 max. So the nice thing about this function is that it only succeeds when the source string can be fully copied to the destination array without overflowing the destination buffer. So this function does one thing and one thing only, which is it copies a string. And if it fails to copy a string for any reason, it fails and provides a return status indicating that it's failed. So there are a number of runtime constraints associated with this function, which again will cause the runtime constraint handler to be invoked. So first of all, neither the source or destination arrays can be a no pointer for obvious reasons. S1 max cannot be greater than rsize max. Again, R values of rsize t that exceed rsize max typically indicate that an error has been made in calculating the size, so that's considered as a runtime constraint error as well. S1 max cannot be 0, and we also want to ensure that we can copy the entire string. So S1 max has to be greater than the amount of characters available in the source string. Otherwise, we're going to be truncating the source string and not copying an entire string. It's also a runtime constraint error if copying takes place between overlapping objects. And if there is a runtime constraint violation, S1 is not a no pointer and S1 max is greater than 0 and not greater than rsize max, the strcopy_s function will also set the destination array, the first character of the destination array, to the no character. So if you go ahead and try to use that, at least it will be a no string. Okay, so let's look at an example of strcopy_s in Visual Studio. I'm going to go ahead and continue, and now I'm at this copy function, so we'll step into the copy function. And this again is similar from the copy function that we saw in the previous sub-lesson when we were using strncopy to try to copy these string literals into these buffers. So again, we have buffers of 16, 16, and 24 characters respectively. And we'll do this first strcopy into this buffer. And what happens here is that we get a runtime constraint handler. So invalid parameter detected in function strcopy_s. And this, of course, is because we installed this invalid parameter handler. So in fact, what happened is that this function failed and we generated a runtime constraint error, and we detected that runtime constraint error and printed out a message in this case. But of course, we could have aborted or performed any other function. So again, that's the nice thing about this function, is here's a case where this copy can almost succeed, but not exactly succeed. So because there's insufficient room in the destination array for all these characters and the terminating no byte character, the copy fails because the string is not properly no terminated, and we get this runtime constraint error. So this is a very safe way to copy a string, and the preferred way to copy a string if you're using statically allocated memory and have an implementation that supports Annex K. ISO IEC TR 24731-2 defines replacements for many of the standard C string handling functions. These functions are based on POSIX functions that dynamically allocate memory to ensure that buffer overflows do not occur. These functions all ensure enough memory is available, except in the case where a call to malloc fails, in which case they'll return some sort of error status. So the ISO IEC TR 24731-2 functions implement the callee allocates caller freeze memory management model. So because dynamic allocation functions require additional calls to free the buffers later, these functions are typically better suited to new development than to retrofitting existing code. The C11 Annex K functions were designed by Microsoft explicitly for the purpose of retrofitting existing code, so they were designed to be very close replacements that could frequently be automatically replaced. So in general, the ISO IEC TR 24731-2 functions provide greater assurance that buffer overflows will not occur because these buffers are automatically sized to hold the amount of data available. So applications that use dynamic memory allocations, however, are more prone to memory exhaustion and other errors dealing with dynamic memory management. So the TR 24731-2 functions include functions such as the strdupe function, which is derived from POSIX. Strdupe returns a pointer to a new string, which is a duplicate of the original string that's passed as an argument, hence the function name strdupe for duplicate. The returned pointer should eventually be passed to free so the storage can be deallocated. The strndupe function is another function derived from POSIX. It's equivalent to strdupe, except it copies at most n plus 1 bytes into the newly allocated storage and ensures that the newly created string is always properly terminated. So another function defined in TR 24731-2 is the getLine function, which is another replacement function for getS. So getLine will read from a stream until it encounters a new line character. So it has this following signature, and you'll see it passes a pointer to char called line pointer, a size, and a stream. So the characters read are stored in the string pointed to by the argument line pointer, and you can supply some memory here initially and it will be resized appropriately, or you can just start by setting it to a no pointer and setting n to 0 or star n to 0, and the function will then allocate the storage and update the size accordingly. So I have this demonstration in a virtual machine. One of the problems is that Microsoft Visual Studio currently doesn't support this getLine function. So we have a main, and just like the previous two examples we looked at, we're calling a get yes or no function. And now we have a response variable, which instead of identifying a statically allocated array is just a pointer to char, and we initialize that to null. And we have also a variable of type size t to keep the size in. So again, we ask the user if they want to continue or not, except now we call the getLine function, and we pass a pointer to our pointer to char and a pointer to our size field, and standard in is the stream from which to read the data. And so if we get a no input, we go ahead and free the storage associated with the response and exit. Otherwise, we still free the storage associated with response, but then we return to the calling function in main. So I'm going to go ahead and exit Emacs, and I'm going to invoke the GCC compiler. And you can see here that we have the wall flag set to compile with all warnings, and it compiles cleanly. And so we can say a.out and go ahead and test this program. So I can say yes to continue, or I can say no to not continue. And of course I can type a really long string, in which case we are hoping there is no buffer overflow, but that the getLine function will allocate sufficient storage to hold all the information I am typing. And you'll see that it does succeed without crashing. And of course that's interpreted as a yes response to continue. So the bounds checking interfaces are an example of caller allocates and caller freeze functions. They can often be used as simple replacements for the original library functions defined in strings.h, and because of this they are often recommended for retrofitting existing code. They are not foolproof, however, because they're still capable of overwriting a buffer if the maximum length of the destination buffer is incorrectly specified. The dynamic allocation functions defined in TR24731-2 and POSIX are typically better suited to new development than to retrofitting existing code. The caller is responsible for freeing the dynamically allocated storage, and those additional calls need to be added somewhere in the logic, so it requires a little bit more consideration.
The C programming standard explicitly identifies over 200 undefined behaviors. Compilers need not diagnose these undefined behaviors, and furthermore have the latitude to assume that undefined behaviors will not occur. Increasingly, compiler writers are taking advantage of undefined behaviors in the C and C++ programming languages to improve optimizations. This can lead to surprising behavior. For example, the elimination of dead code that the programmer added to some purpose. In this lesson, you learn what undefined behavior is, how the C standard identifies undefined behaviors in the language, and the latitude it grants to compilers in dealing with undefined behaviors. You also learn about common compiler optimizations, and how these optimizations can produce unexpected behaviors. Topics include undefined behaviors and the as-if rule, constant folding, algebraic simplification and pointer arithmetic, hoisting of loop invariant computations, dead code removal, and aliasing.
So the first question is, why understand optimizations at all? The problem is that increasingly compiler writers are taking advantage of undefined behaviors in the C and C++ programming languages to provide better optimizations and improve the performance of the code. And generally speaking, that's a positive step, but frequently these optimizations interfere with the ability of developers to perform cause-effect analysis on their source code. In other words, making it increasingly difficult to look at source code and understand what that code is actually doing. And that's true of both human programmers and automated analysis tools. So consequently, these optimizations eliminating causality in software, increasing the probability of faults, defects, and vulnerabilities being left undiscovered in the code. So to understand optimizations, we first have to understand undefined behaviors. Behaviors are classified as undefined by the Standards Committee to give the implementer license not to catch certain program errors that are difficult to diagnose, possibly because they're undecidable problems. Also to avoid defining obscure corner cases which favor one implementation strategy over another. So for example, the Java standard specifies that taking int min and taking the remainder when divided by -1 should equal 0. But the C standard defines that as undefined behavior, so that if your processor, for example, the Intel processor, is going to fault on that instruction, the C language isn't going to require you to write a test to avoid that particular case and return a 0. Instead, it'll allow the implementation to behave in a characteristic manner of that implementation, which in that case is default. The third reason behaviors are defined as undefined is to identify areas of possible conforming language extension, meaning these are really hooks put into the standard by the committee to allow implementations to augment the officially undefined behavior. An example of that might be the file modes for fopen. So implementations, when they encounter undefined behavior in code, they can ignore that undefined behavior completely with unpredictable results. The saying in the C Standards Committee is the compiler's free to then go off and play the game of life. They can also behave in a documented manner characteristic of the environment, for example, faulting on integer division overflow or remainder. And the third possibility is to terminate the translation or execution with a diagnostic. So the basic design of an optimizer for C compiler is largely the same as an optimizer for any procedural programming language. The fundamental principle is to replace a computation with a more efficient method that computes the same result. So the C standard specifies the results of computations as if on an abstract machine, but the methods used are not specified. So in the abstract machine, all expressions are evaluated as specified by the semantics of the language. An actual implementation does not need to evaluate parts of an expression, for example, if it can deduce that the value resulting from that expression is not used and that there are no needed side effects such as calling a function or accessing a volatile qualified object. The compiler's optimizer is really free to choose any method that produces the correct result that's required by the abstract machine. So the as-if rule gives compilers leeway to remove code that's deemed unused or unneeded when building a program. And again, this is commonly referred to as the as-if rule because the program must run as if it were executing on the abstract machine. But again, the methods aren't specified. So this is typically beneficial. For example, it allows the compiler to remove code that's not needed, but occasionally that code does perform a specific purpose, and silently eliminating it from the executable is detrimental to the execution of the program. So Compilers can take a variety of strategies. So these are sort of high-level strategies that a compiler might take. Typically, compiler writers are very practical, so they tend not to have a firm fixed policy about anything. They'll take whatever action seems appropriate at that particular occasion. So it's hard to assume that a compiler is going to take any particular approach, but in general, there's the hardware behavior model, which states that the compiler is just going to generate the corresponding assembler code and let the hardware do whatever the hardware does. And for many years, this was sort of the near universal policy, so several generations of C programmers have assumed that C compilers behave this way. A second possibility is super debug. And this is basically an intensive debugging environment where the compiler tries to trap nearly every undefined behavior. The problem with this policy is it severely degrades the performance of the application, so it is seldom used for building real applications. It's more for debugging and testing. The third model is total license, where the compiler treats any possible undefined behavior as a can't happen condition, permitting very aggressive optimizations. So constant folding is a simple optimization where constant expressions are simplified at compile time. So terms in constant expressions can be simple literals, such as the integer 2, variables that are never modified, or variables that are explicitly marked as constant. So constant folding is performed by Visual Studio 11 Beta and most compilers, even when the optimizations are disabled. So we have a simple program here where we're going to perform a remainder operation and print the result, and then we're going to take two arguments from the command line and perform a second remainder operation, and that's all. So let's go ahead and build this, and you'll see that at the highest warning levels this program builds cleanly, and now we can go ahead and debug. So we've advanced to this first breakpoint, and all we're going to do here is perform a remainder operation. We're going to take the int min remainder -1. So let's look at the assembly code here. And you can see what's happening is that there's been constant folding performed by the compiler that evaluated this expression during compilation time and determined that this was going to result in the value 0. So rather than perform the operation at runtime, which would require some overhead, it just simply gives the result of this operation as 0, so it assigns the value of 0 to I. And so when we print I here, we'll see that the result is 0. So let's go back to the C code, and we'll go ahead and print the result, and I could pop up the output window, and you'll see in fact that the result is 0. So we'll continue, and we'll read two arguments in from the command line. So these arguments, arg1 is really int min, which is the same value that we used here, and arg2 is -1, which again is the same value that we used here. So let's look at the disassembly. So now we see something a little different, and of course the reason we see something different is because arg1 and arg2 are unknown at compilation time, so there's no simplification, no constant folding possible. So instead we're actually going to move the value from arg1 into the EAX register, and we'll do a CDQ, so we'll sign extend that into the high order bit into the EDX register, and we'll perform this IDIV of that value with arg2. And here you see something different because we've now had an overflow in the IDIV instruction trying to calculate the result. So this is a consequence of undefined behavior, and it's actually always undefined behavior. So signed integer overflow is undefined behavior, but the compiler has some latitude in what sort of actions it takes. So you see here it will actually insert the mathematically correct result of 0, but here, because it's relying on the Intel IDIV instruction, it's going to generate a fault at runtime. So the problem in this case is, say you're trying to test out on your compiler what is the result of taking int min and taking the remainder -1. If you just write a very, very simple test, which a lot of people will, you'll see that it always produces a 0, but in fact the operation does fault at runtime. So the lesson here is you have to be very careful in writing your test and make sure that you account for any optimizations that might be performed. And the easiest thing to do is probably look at the generated assembly code and make sure that you're testing what you think you're testing. Pointer arithmetic in C involves adding or subtracting an integer to or from a pointer. The C standard states that when an expression that has integer type is added to or subtracted from a pointer, the result has the type of the pointer operand. So an expression like p sub n, which is used to access an array element, is actually translated into p plus n dereferenced. So the array notation is just sort of a thin veneer over pointer arithmetic. And of course, in both cases, n is scaled by the size of each element in the array. The C standard also states that if both the pointer operand and the result point to elements of the same array object, or one past the last element of the array object, the evaluation shall not produce an overflow, otherwise the behavior is undefined. So what this means is that we can form a pointer to each element in the array up into including a pointer that points to the element that's one past the end of the array, but we can't form any other pointer. So we can't form a pointer that's, say, two past the end of the array or even before the array. The C standard goes on to say, if the result points one past the last element of the array object, it shall not be used as the operand of a unary dereference operator that is evaluated. So what this means is, although we can form all these pointers to each element, including this one that's one too far, and we can dereference each of these pointers that point to all the elements in the array, but even though we can form this pointer, it's undefined behavior to dereference this pointer because you're referencing an object that's outside the bounds of the array. So a programmer might want to code a bounds check to make sure that an access isn't occurring beyond the bounds of the array by setting a char pointer to point to the start of the array and a second pointer max to point to the end of the array, and then taking a size t-value len to determine which array element to access. So the check would be written to say if pointer plus len is greater than max, where we're trying to form a pointer that's beyond the end of the array, and consequently that's an error condition that needs to be reported. So that looks fine, but no matter what model is assumed here, whether it's a hardware model or super debug model or total license model, there's a bug in this code. And the bug is that if len is a very large value, it can cause pointer plus len to overflow, which results in undefined behavior. So under the hardware behavior model, the result would typically wrap around in memory, pointing to an address that is actually lower in memory than the original value of pointer. So in order to fix this bug, an experienced programmer who's internalized the hardware behavior model of undefined behavior might write a check that looks like this, where they'll say pointer plus len is less than pointer. Now what this does is it should detect wraparound by determining if the resulting pointer is actually less than the value of pointer added to the len. So this term can be added to the test in order to determine if wraparound has occurred. So this looks pretty good for, again, experienced programmers who's used to this hardware model of wraparound. However, compilers that follow the total license model can optimize out this first part of the check, basically leaving the whole bounds check defeated. So I have a very small program here, and basically what we were just looking at, we've got a main, and we've got a character array of 10 elements, and we have a pointer PTR to the first element in the array, and a pointer max to the last element of the array. And so we're going to take a size as a command line argument and just print it out so we can see what it is. And then we're going to perform this test. We're going to test for wraparound, and then we're going to test to see if pointer plus len is greater than max. And if this test is true, we're going to print out overflow, meaning we're assuming that this first part of the test is what caught, and then we're going to return exit failure. Then, if it doesn't catch this, we're just going to go ahead and access the array. So in place of the actual array access, I just put a print statement so we can easily see it. So I'm going to exit this, and we'll go ahead and compile the code. And I'm going to compile the code here with no optimization. So we're going to use the wall flag but not include any optimization. So you can see there's no compilation warning, so it compiles cleanly. And let's go ahead and now run the code. And I'll run it first with the value 2. So 2 is well within the bounds of the array. And so what we see is that len is 2, and you can see that we don't print error overflow and exit. Instead, we go ahead and perform the array access, and everything is as it should be. So let's now go ahead and run the same program with a much larger value. And now, again, so in this case, we see the very large value for len, and the wraparound is detected, so the if clause is true, and we print out error overflow and then exit. Okay, so again, everything is as it should be. So let's go ahead now and recompile the program, except this time I'm going to add a flag to build at O2. So now we have an optimized build. And if I run this with the value 2, we can see that again the test is false and we access the array, and that's fine because 2 is within the range of the array. And let's now run it with this larger value of 2 billion. And what happens here is we can see that len is this large value, but then we see that the array access is occurring. So this is the peculiar behavior, because when we ran it just a short while ago, you can see still on the screen that we were detecting an overflow. However, when we compile this at O2, the wraparound check is actually removed because it's undefined behavior. So you can see that the version of GCC that we're running here is 4.24, which is actually one of the first versions that this behavior occurred in. What's going on here is that this optimization of eliminating this test is allowed because if pointer plus the unsigned len compares less than pointer, that means undefined behavior has occurred during the calculation of pointer plus len. We've clearly formed a pointer that doesn't point to another object in the array or one past the end of the array. The compiler, under the total license model, can assume that undefined behavior never occurs. Consequently, this test to see whether undefined behavior did occur, whether wraparound occurred, is dead code and it can be removed. So this particular optimization is just algebraic simplification. So algebraic simplification says that optimizations may be performed for comparisons between some pointer value p plus some integer value v1 and that same pointer p plus v2, where p is the same pointer and v1 and v2 are variables of some integer type. The total license model permits this comparison to be reduced to a comparison between v1 and v2. However, if v1 and v2 are such that the sum with p overflows, then the comparison of v1 and v2 will not yield the same result as actually computing p plus v1 and p plus v2 and comparing the sums. So the interesting takeaway here is that because of possible overflows, computer arithmetic does not always obey the algebraic identities of mathematics. So in our example, we were again saying if pointer plus len is less than pointer. So this particular expression seen here can be translated to pointer plus len is less than pointer plus 0. So this is a valid transformation. And what we have now is we have a comparison of p plus v1 compared to p plus v2. And algebraic simplification says that we can reduce this to a comparison between v1 and v2. However, when you look at this, we're now asking if len can be less than 0, and this is impossible because len is an unsigned number. So clearly this is dead code and it can be eliminated from the executable. So this problem is actually pretty easy to fix once it's called to the attention of the programmer, such as by a diagnostic message when dead code is eliminated. The problem, of course, is that it's not always easy to recognize this problem, and you don't always see a diagnostic. For example, in the example we just looked at, Wall did not produce a diagnostic for this. So, for example, if it's known that pointer is less than or equal to max, then a programmer can write this test as len greater than max minus pointer. And this expression eliminates the possibility of invoking undefined behavior. So this will definitely be translated into object code. Okay, so the particular details of GCC in this case is that the behavior of pointer overflow to this optimization to remove these checks occurred starting in versions 4.24, 4.31, and 4.40, and all subsequent versions where 4.2.x where x was greater than or equal to 4, 4.3y where y was greater than or equal to 1, and 4.z where z is greater than or equal to 4. The optimization is performed by default at O2 optimizations and above, including optimizing for space. It is not performed by default at O1 or O0. The optimization may be enabled for O1 with the F-strict overflow option or disabled for O2 and above with the F-no strict overflow option. Cases where optimization occurs can be detected by using a W-strict overflow equals n, where n is set to a value greater than or equal to 3. However, by default, W-strict overflow is set to 2 as part of the wall flag, so just using wall is insufficient to catch this particular problem.
So, loop invariant code consists of statements that can be moved outside the body of a loop without affecting the semantics or behavior of a program. So loop invariant code motion, it's also referred to as hoisting or scalar promotion. It is a compiler optimization that performs this movement automatically by the compiler. So loop invariant code which has been hoisted or moved outside of a loop is executed less frequently, and that provides an obvious speed up. So there are some constraints on the sort of code motion that compilers are allowed to perform. So for example, if you have an implementation that detects signed integer overflow, those implementations are constrained not to transform a program that doesn't get an integer overflow into a program that does get an integer overflow. So you might recall from our earlier sublessons on integer operations that the division and remainder operations on the Intel platform do detect signed integer overflow with a division fault. So those would be examples of operations that could not be moved if they were to transform a program into one that would have an overflow. So to give an example of this, let's imagine we have a implementation in which all signed overflow is detected, even addition. So if we had a small program fragment that was testing if some integer, signed integer value z is less than int max before adding 1 to z, this program is guaranteed to be free from integer overflows because the only possible value of z which could result in an overflow is z equals int max, and we've tested to make sure that it's less than int max. So a compiler would consequently not be allowed to perform a transformation where the addition is hoisted outside of the conditional and the result stored in a temporary variable followed by the test, unless the implementation can prove that this is not going to introduce an overflow into a program that previously didn't have an overflow. So we're going to look at a more detailed example in Visual Studio, and we'll have a sub-expression, which is SI1 remainder SI2, that's loop invariant, and can consequently be hoisted outside of a loop. So here's the program, and I'll go over the program quickly. We have two variables, SI1 and SI2, which we're taking from the command line so that they're not subject to constant folding. Then we print out a log message. Then we have a loop for I equals 0 to I less than 100. So, of course, having a loop here is a magnet for compiler optimizations because you get a large benefit from optimizing code that's executed repeatedly. And within this loop, we have this expression where we're adding result to result plus I plus SI1 remainder SI2. So SI1 remainder SI2, of course, is a loop invariant sub-expression because neither SI1 nor SI2 is modified during the execution of this loop, but it would definitely be executed along all paths. And again, we can't just resolve this sub-expression through constant folding because the compiler doesn't know what the values of SI1 and SI2 are because they're going to be taken from the command line. So after this, we print out a third log message, print the result, and then exit. So let's go ahead and take a look at this. So first of all, I'm going to show you that we're going to compile this program at maximum speed 02. So most of the programs we've looked at so far have had optimization disabled because that makes it easier to see what the assembly instructions are doing. But we want to see the behavior of this code when optimized. So we're going to build at 02. Let me do a quick clean, and then we'll do a build of the solution. And you can see here that this code in fact is compiling cleanly. Let's go ahead and start debugging. Okay, so I'm going to go right to the disassembly so we can get a sense of what's going on here. So we have some instructions here associated with the log message. And we come down here and we have the idiv instruction. So this is the idiv instruction. We're dividing arg1 by arg2 or si1 by si2. And now we're going to print out the second log message. We have our little conditional based on argc. And here's the full expression. So here we're going to just do the addition part of the expression. And now we're already up to the point where we're calling the puts function to print the third log message. We're incrementing EDI and ESI. And now we're going to compare EDI to 64 hex or 100 decimal to see whether we've completed the loop. So EDI contains the loop counter. And it's going to turn out that we haven't finished yet. So we're going to jump back to this point earlier in the program. So if you look at the point we're jumping back to, it's right here where we're about to print the second log message. So you can see that the instructions to perform the remainder operation between SI1 remainder SI2 is performed once prior to the beginning of the loop. So that's an example of code motion or hoisting of loop invariant sub-expressions. So they're only performed once and you get a performance improvement. So let's go ahead and stop debugging. So we're going to look at something slightly different in this program, which is the log messages 1, 2, and 3, which are being printed out. Log message 1, of course, is printed out once before the loop is executed, and log message 2 is printed out inside the loop, but before the loop invariant sub-expression, and log message 3 appears after the loop invariant sub-expression. So let's go ahead and bring up the project window. What I'm going to do initially is I'm going to turn off or disable optimization and save that change. And we'll go ahead and do a clean and a build. It still builds cleanly, of course. And I'm going to go ahead and just start debugging that. And I'm going to go and just hit continue right away and move to the end of this loop. And now I want to look at the output window. And what you'll see in the output window is that we have log message 2 and log message 3 have been output to the console 100 times for each iteration of the loop. And if we scroll up to the top of the screen, we can see that log message 1 was in fact printed once prior to beginning the loop. So we've got all the correct behavior that we're expecting there. So let me stop debugging. And we'll go to the properties page again, and now I'm going to make two changes. One is I'm going to turn optimization back on, so we're optimizing again at level 02 for maximum speed. And I'm also going to go to the debugging window, and I want to change the command line inputs to this program so that now the first argument is int min and the second argument is -1. So these two arguments, of course, will cause our remainder operation to result in a division error and a fault. So we'll go ahead and save those changes. We'll do a clean build here, and we'll rebuild the code with the new optimization levels. and then we could go ahead and start debugging. Okay, so this time I'm going to try to single step through. So we're going to print the first log message, we're going to enter the loop, and suddenly we've got our division fault. So let me go ahead and break, and I'm going to look at the output window. And what you'll see in the output window is that we've only printed log message 1. Okay, so how do we explain this? It's really quite simple. What we've already seen is that this sub-expression SI1 remainder SI2 is loop invariant, which means it can be hoisted once up above the execution of the loop, and we saw that in the assembly code. What this means is that the compiler can also hoist inevitable undefined behavior, such as this potential fault, before output statements. And the consequence of that is when you look at this program, normally you would expect this log message to be followed by the second log message followed by this operation. But because of code motion, this fault can actually occur prior to this log message being printed out or any other sort of output. So the existence of undefined behavior anywhere in the program, inevitable undefined behavior anywhere in the program, can result in programs crashing or terminating much earlier than you might expect. And it's also possible that these inevitable undefined behaviors could be hoisted before volatile qualified object accesses as well. So in the information security area, we might want to prevent information leakage, such as password, encryption keys, or private information such as credit card information or medical data. We might want to prevent that information from leaking outside of a program by clearing sensitive information in memory after we're done using it. And this might be accomplished, for example, with a call to memset. So let's look at a Visual Studio program. And this Visual Studio program is a bit longer than other programs that we've looked at, but it's conceptually pretty simple. So we have a small function called getPassword, and what I've done is I've just implemented 6 different versions of this function, trying different solutions. So in general, the getPassword function, we'll look at getPassword1. It has a character array of 64 bytes that's declared on the stack. And we use the fgetS call to read in the password from the console, from standard in. And then we use the stirchar function to replace the end of line character with the string termination character. And then we have some code which would theoretically verify that the password is correct. And after we've completed that verification process, we want to clear the password from memory so it's not accidentally leaked. And in this function, we're going to use a call to memset to accomplish that. And then presumably we can return some indication of whether or not the password was successfully verified. So let's go ahead and build this program. You can see we have optimization turned off. So we'll build the solution. And this solution generates buckets of warnings. And these warnings are all a result of the windows.h file, which we've included, which doesn't build very cleanly, unfortunately. We've compiled the program. Now we can start debugging. And I'm going to step into this getPassword1 function. And we'll read some input from the command line. So I'll type in some data that could be a password. And let's switch over to the assembly code so we can see what's going on. So we're calling the stirchar function. We're replacing the line termination character with the string termination character. And now we're calling the memset function. So if you see down here in locals, you'll see the password data that I typed in at the command line. And on this line, we're about to call memset. And that call clears the memory associated with password, so everything is working just as we'd like it to work. Now, compilers can perform an optimization called dead code removal. So this is when compilers remove code sections if the optimizer determines that removing that code will not alter the behavior of the program. So for example, an optimizing compiler could decide in the program that we just looked at that PWD is not accessed again after the call to memset. So therefore, the call to memset is unnecessary and can be optimized away. So what the compiler doesn't realize, of course, is that we put that call there for the purpose of clearing that memory, so that memory wasn't subsequently leaked. So let's go back to Visual Studio again. And what we're going to do is change the properties of this program. So we're now going to compile it at 02 for maximum speed. And stop debugging. We'll clean the solution and we'll build it again. And so we got all those warnings that we got last time from including the windows.h file and ignored, but we also got 3 additional warnings. And the compiler here is actually just warning us that they're inlining some of the functions we've written, including getPassword1, which we just looked at, and also getPassword2, and a function called secureMemset. Okay, so let's go back to debugging the program. I'll start debugging. And if you recall, we inlined this getPassword1 function. So let me just go to the assembly code because I can't really step into that function anymore. The code's going to be just inlined. So we'll step through this, and I'm just going to continue until the call to fgets. We'll provide some command line input for the password, come back to the program, and continue executing. And so you'll see we get to the point where we've returned from that function, and missing is the call to memsetS. So at no point in this getPassword function are we now calling memsetS and calling the memset function. So the problem is that because the storage referred to by PWD is not referenced again in this function, and the duration of this variable is only the call of the function, the compiler can see that PWD is not referenced again, and consequently it can perform dead store removal and eliminate this call to the memset function. Let's continue and look at the call to getPassword2. So the getPassword2 function has a small change, which is we're now, instead of calling the memset function, we're going to try calling the zero memory function. So the zero memory function is not defined by the C standard, but it is an implementation specific function provided by many versions of Microsoft Visual Studio. So I'm going to look at the assembly code, and we're going to go ahead and implement the getPassword2 function, which, as you recall, was also inlined. So we're just going to step through this. And if we go through a couple instructions, we'll get back to the point where we're looking for input from the command line. So we'll type in some more data that might look like a password and get back to the assembly instructions and continue executing. And you'll see again that we're about to leave the code for the getPassword2 function and just print out that the access has been granted. So again, what we could see with getPassword2 function is it's equally ineffective. So just like the memset call, Microsoft Visual Studio is going to optimize out the zero memory call. So replacing memsetS with zero, a call to zero memory, doesn't buy us anything at all. Okay, so let's continue executing. And now we're going to call the getPassword3 function. This wasn't inline, so I'm going to step into it. And the change in this function is that we've replaced the call to zero memory with a call to another Microsoft Visual Studio function called secure zero memory. So the Microsoft Visual Studio secure zero memory function guarantees that the compiler does not optimize the call out when zeroing memory. So let's take a look at what that might look like. So we'll look at the disassembly, and again we'll just step through this quickly until we get to the fgets call. We'll provide some input that looks like a password, and then we'll continue executing. There's the call to stir char, and here's the call to secure zero memory. So we can see in this case that there's some actual instructions which have been generated here. So we're going to execute these instructions, and you can see down here is the PWD array. So as we execute these instructions, you'll see that these character elements in the array are being zeroed out on each iteration. So in fact, the compiler has generated a loop to clear out the array according to the semantics of the secure zero memory function. So this solution was successful, and the only problem with this solution again is it uses a non-standard secure zero memory function. Okay, so let's continue executing, and next we're going to look at the get password for function. So let me step into that. The get password for function is going to try using the memset function again, except this time we've used the optimize pragma. So we're turning optimization off prior to executing this function, and then we're turning it on again following the function. So basically we've disabled optimization for the get password for implementation. So the pragma directives again instruct the compiler to avoid optimization in the enclosed code. The pragma directive is supported on some versions of Microsoft Visual Studio and may also be supported on other compilers. Pragmas, by their very nature, are non-standardized. Pragma is really a standard mechanism for performing non-standard extensions. So let's take a look at this, and we'll look again at the assembly code. So I'm just going to step through this pretty quickly till we get to the call to fgets. We'll type in some more data that provides the password information, and we'll continue executing. There's the call to stir char, and here's the call to memset. And so you can see the call, and here's the PWD field. So you can see that the call to memset is right here. So this call has not been cleared out. The compiler has included it because we've told it not to optimize. So when we execute this instruction, you'll see that the PWD field is cleared as desired. So here's another example of a solution that works. Again, it might not work on all platforms because we're using a non-standard pragma called optimize. And the further disadvantage of this solution is that it really can be inefficient because we've turned optimization off. And so there might be other optimizations that can be performed on this function that we've disabled. But we do get the desired behavior on this particular compiler. Okay, so let me go back to the Visual Studio slides. And before we look at the next solution, I want to talk about volatile qualified types. So an object that has a volatile qualified type may be modified in ways unknown to the implementation or have other unknown side effects. Consequently, the volatile keyword imposes restrictions on access and caching. Now, in the absence of this qualifier, the contents of a designated memory location can be assumed to be unchanged except for possible aliasing. So that means, for example, the PWD field, the compiler can see that memory is not going to be changed in any way that it's unaware of. But if you make that memory volatile qualified, you're telling the compiler that memory might be changed in a way that is not apparent to you, and you have to assume you don't know what values are stored in that memory. So, according to the C standard, access to volatile objects are evaluated strictly according to the rules of the abstract machine. So that's further explained in the C99 rationale, which says no caching through this L value. Each operation in the abstract semantics must be performed. So that is, no caching assumptions may be made since the location is not guaranteed to contain any previous value. So what that means is every time you want to access that variable, you have to read the memory, and then when you're storing a value to that memory, it has to be stored immediately. So for example, if we had a loop counter I that was not volatile qualified, it's quite likely that the compiler will load that into a register and just increment that loop counter on each loop increment. But if that loop counter were volatile qualified, we wouldn't be able to store that counter into a register. So we would have to read it from memory, increment the value, and then store the incremented value back out to memory on each iteration of the loop. So consequently, it's much less efficient than not having a volatile qualified object. So let's go back to Visual Studio. And as you might guess, we have a solution implemented by our next function, getPassword5, which uses volatile qualified objects. So the getPassword5 function calls memset again, and following the call to memset, we are going to read 1 byte from the PWD field, and we're going to read it through a volatile qualified pointer to char. And then we're going to write that byte back into the same memory location, again through a volatile qualified pointer to char. So the goal here is that we're trying to touch the PWD memory following the call to memset. And what we're hoping this will accomplish is that the compiler will no longer be able to perform dead store removal because we are in fact using that memory again following the call to memset. So let's go into the disassembly and see what actually happens. So I'm going to step through again quickly until we get to the call to fgets, provide some password data. We'll come back to the program. You'll see the call to stir char. And if we continue, you'll see down here again is our password. And here's our call to memset. So this approach has actually succeeded because the call to memset is still here, and when I call memset, you'll see that the password memory is cleared, and we'll then perform this operation where we read a byte and write the byte back. So this solution also succeeded in clearing the memory. Now, the only problem with this solution is that on some very clever implementations, the compiler might actually only nullify the first byte in PWD and leave the remainder of the information intact. And that's because it can see that we're only using that 1 byte. So that's a very clever optimization. And what you'll see is that the compilers can be really, really clever at defeating your attempts to perform a relatively simple operation like clearing memory. So let's continue. So we're going to now demonstrate a final version of the getPassword function called getPassword6. This one, as you recall, was not inline, so I'm just going to step into it. And this function is going to use a volatile type qualifier to inform the compiler that the memory should be overwritten and that we shouldn't optimize out the call to the memset function. So instead of the memset function, we've implemented our own version of memset called secure memset. So what secure memset is going to do is it has a similar signature to memset function. It takes a pointer to a destination array, some memory to fill the contents of that array with, and the size of the array. So we're going to take the pointer v to the destination array, and we're going to assign it to p, which is a pointer to a volatile unsigned char pointer. So it makes sense for this to be unsigned char type because unsigned char allows you to access only the underlying bits of the array. So we have a small loop where we start with n, which is the size of the destination array, and count down to 0. And for each element in the destination array, we overwrite the contents of that element or that byte in storage with the value c cast to an unsigned char in the same way the memset function works. So this is going to clear the array. And the hope here again is because we're writing through a volatile qualified pointer that the compiler will not be able to optimize out these instructions. And we've furthermore tried to isolate this code in its own function, which makes it less likely. And if we want to make it even less likely, we can take this function and move it into a different compilation unit. So let's go ahead and look at the disassembly, and we'll step through this and see what sort of behavior we're getting. So I'm just going to go quickly until we make the call to fgets. I'll provide some password data again, and we're back to the code. So if we continue to run, you'll see the stir char call, and here's the secure memset function. So we have the password array displayed below in the locals, and as we step through this code, you'll see that we're beginning to clear the memory associated with this, with the PWD array. So this code looks really exactly like the secure zero memory function that we saw earlier. So this solution again has been successful. And the advantage of this solution is we're using all standard calls. We've provided our own secure memset function, but there are some disadvantages too. So let's go back to PowerPoint. So the secure memset solution prevents clearing of memory from being optimized away, and it should work on any standard compliant platform. There are some problems with some compilers that violate the standard by not always respecting the volatile qualifier. So you should be you should be careful with your compiler and make sure that this is in fact going to work. The more generic problem with this solution is that it might be inefficient because again the volatile type qualifier prevents the compiler from caching any of these values, and that can frequently make the code quite inefficient. So for example, some compilers might replace a call to memset with an equivalent assembly instruction that's much more efficient than the memset implementation, say a block clear instruction. And implementing the secure memset function as we just showed you in this previous example might prevent the compiler from using the optimal assembly instructions and result in less efficient code. So as a result of all this, the WG14 C Standard Committee introduced in C11 the memset s function. So memset s is included in Annex K, which is a optional but normative annex to the C standard. So the memset s function is very similar to memset, except that unlike memset, any call to memset s is evaluated strictly according to the rules of the abstract machine. So that's basically the way you express the concept in the C standard that this code shouldn't be optimized. So again, it assumes that the memory indicated by S and N may be accessible in the future and therefore must contain the values indicated by C. So again, this description says is that calls to memset s cannot be optimized out of the code. So memset s is now a standard mechanism, although it's in an optional annex, but it is a standard mechanism to clear memory in a way that it's guaranteed to be cleared, and also it can be done in as efficient a way as possible because the memset s function is is known to the compiler, and it can generate optimal assembly instructions as a result. So two types in C are compatible if their types are the same. Rules for determining whether two type specifiers, type qualifiers, or declaratives are compatible are described in C standard. So in general, two types do not need to be identical to be compatible, but if there are no rules allowing types to be compatible, they are not compatible. So for two qualified types to be compatible, Both must have identically qualified versions of a compatible type. Of course, the order of the type qualifiers within the list of specifiers or qualifiers do not affect the specified type. For two pointer types to be compatible, both must be identically qualified and be pointers to compatible types. For two array types to be compatible, both must have compatible element types, and if the size specifiers are present in both arrays and are integer constant expressions, then both size specifiers must have the same constant value. So in general, the compatibility rules in C are quite strict. So for function type compatibility, a function type declared using the new prototype style declaration, and by new we mean as of 1989. So for example, int tree int x is compatible with another function type declared within a function prototype if the return types are compatible, the parameters agree in number, including an ellipsis if one is used, and the parameter types are compatible. So for two structure, union, or enumerated types declared in separate translation units to be compatible, they both must be declared with the same tag or both be declared with no tag. There must also be a one-to-one correspondence between their members, such that each pair of corresponding members are declared with compatible types. For two structures to be compatible, corresponding members must be declared in the same order. For two structures or unions to be compatible, the corresponding bit fields must have the same widths. And for two enumeration types to be compatible, corresponding members have to have the same values. So the following types, which may be confused to be compatible, are really not. So for example, unsigned int and int types are not compatible. The char, signed char, and unsigned char types are not compatible, even though, as we've seen in an earlier lesson, that char is going to have the same type and representation and size as either signed char or unsigned char. Int and long types are not compatible, even if they have the same representation, for example, on x86-32, where they're both 32-bit signed types. So let's take a close look at int and long compatibility. Int and long keywords denote type specifiers. There's only one additional rule in the C standard, which states that each enumerated type is compatible with char, a signed integer type, or an unsigned integer type. So, since there are no rules allowing int and long to be compatible, they are not. So, even though this is about C, it's interesting to note that C++ has no notion of type compatibility aside from the types being the same. So type checking in C++ is stricter than in C and requires identical types in situations where C would only require compatible types. So the next concept to look at is effective type. The purpose of the effective type rules is to impute a type dynamically to a dynamically allocated storage, for example, allocate it with malloc, calloc, realloc, or aligned alloc. The effective type of an object for an access to a stored value is the declared type of the object, if any. However, allocated objects have no declared type. If a value is stored into an object having no declared type through an L value having a type that's not a character type, then the type of the L value becomes the effective type of the object for that access and for subsequent accesses that do not modify the stored value. So that simply says that if you copy an object with a type into an object with no type, that untyped object gets the new type. So for example, if a value is copied into an object having no declared type using memcopy or memmove, or it's copied as an array of character type, the effective type of the modified object for that object and for subsequent objects that do not modify the value is the effective type of the object from which the value is copied. For all other accesses to an object having no declared type, the effective type of the object is simply the type of the L value used for the access. So that basically saying that it can be whatever it is that you want it to be. So let's look at some examples of effective types. So we have a structure here that has a char, an int, a long, and a double, and we'll just initialize those values respectively to 1, 2, 3, and 4. So if we dynamically allocate storage of the size of this struct
and we assign it to a char pointer p, the type of this object following this assignment is none at all. So the type referenced by the pointer p, this dynamically allocated chunk of storage, has no type. So if we allocate another chunk of storage, assign it to p0, and then we copy using memcopy into this allocate storage referenced by p0 from struct s, and we'll copy the size of s. Following this memcopy, the effective type of the object referenced by p0 assumes the type of the object from which it was copied, which is struct st. So for another example, we'll allocate some storage and we'll assign it to a pointer p1 to a void type. So if we then perform a memcopy into the storage, again of the address of this struct s, the effective type of the object referenced by p1 following that copy is struct st. However, if we copy into the same storage referenced by p1 from s.I being the integer field within the structure, the effective type of the storage referenced by p1 is now type int. Now, if we take that same address, the address of the int field, and we cast it to a pointer to float, and then copy that storage into p1, the effective type of the storage referenced by p1 is now float because we cast it or converted that information to type pointer to float. So if we take another pointer, p2, which is also pointing to void type, allocate some storage, and we do a memcopy, except we cast this memcopy to void star. In this case, the storage referenced by p2 still has an effective type of struct st because this conversion to void star does not void the effective type of the object because void star obviously has no type. Very similar example, we'll do a memcopy of the same structure but we'll cast it to char star. And once again, this does not change the effective type of the object because casting to a pointer to char is roughly the same thing as casting to a pointer to void. So in this last case, we're going to allocate one last piece of dynamic allocated storage referenced by p4, and we're just going to cast p4 to a struct st pointer and then assign it to s. So again, this assignment is sufficient to give the object referenced by p4 the effective type of struct st. Okay, so all of that type compatibility and effective type brings us to the point where we can describe the aliasing rules. So a pointer is an alias of another pointer when both refer to the same location in memory or object. Now, an object's stored value can only be accessed by an L-value expression that has a type that's compatible with the effective type of the object. Or, and this is where compatibility rules, this is where aliasing rules relax the requirements of type compatibility. So you can also alias an object through an L-value expression that has a qualified version of a type compatible with the effective type of the object, a type that is the signed or unsigned type corresponding to the effective type of the object, a type that is the signed or unsigned type corresponding to a qualified version of the effective type, or an aggregate or union type that includes one of these types among its members, including recursively a member of a subaggregate or contained union, or finally, an object's stored value can be accessed by an L-value expression that has a character type. Okay, so let's look at an example within Microsoft Visual Studio to see more about how this affects programs. Okay, so we have a slightly more complicated example here to step you through the aliasing rules, but hopefully you'll find this informative. So let me start by describing this a little bit. We have a main, and we've declared some variables up here.
including A and D. So A and D are both values that we're going to take from the command line, and this is so there's some non-deterministic aspects to this that the compiler has to generate code to determine at runtime rather than just using all constants, so the optimizer will just figure out what the solution is, and we won't be able to see what type of code is really going to be generated. And we've declared two arrays, this double array, D array, and this scary array, and I'll describe both of these in more detail. So the idea really is that we're going to look at two different versions of a function, f1 and f2, and these two different functions are similar but different. So the f1 function takes a pointer to an int, a pointer to a double, and a double. And this function is basically going to initialize an array of double referenced by PD, where PI refers to the bounds of the array, and D is the value that's going to be used to initialize the array. So we have a loop for I equals 0 to I less than the bounds of the array specified by PI, referenced by PI, and on each iteration of the loop, we're going to initialize the array element at PD with the value stored in D, and then increment the pointer to point to the next element in the array, and then we'll initialize that element in the array. So let's go ahead now and take a look at this. So I'll show you real quickly that we are building this at optimization level 02 for maximum speed, and that we are compiling with warnings enabled. So let me go ahead and clean the solution, and then we'll do a build. So you can see that this code builds cleanly at warning level 4. So let's go ahead and start debugging. So we're up to this point where we're going to invoke the array, and we're going to pass it the address of A, which is the argument we passed in for the bounds, which is 10. And we're going to pass it a pointer to D array, so we're going to pass it this array of 10 doubles, and we're going to pass it D, which is another argument passed in on the command line, and this value happens, this object happens to have the value 7.4. So let's look at the disassembly code, because it's really hard to look at the source code in this case and gain any understanding of what's going on because the code has been optimized. So here we're going to start by testing EBX. Now EBX has, let me go ahead and hit continue. So EBX has the value 10, which is, or hex A, which is the bounds of the loop. So you can see here it's 10. I'm going to switch back to decimal to display, so it's a little bit easier to read up here. So you can see clearly this has the value 10. So we're going to test whether the loop is complete. It's not. So now we're going to move the value stored in D, which is 7.4, into the XMM0 register. And now we're going to load a value into ECX. That value is going to be based on EBX, which is the loop counter of 10, times 8, which is the size of each element in the array, which is of type double. And we furthermore have a little bit of a modification or a shift right of this value, and this is to account for the number of moves that have to be made to initialize the array with the value stored in D. We're now going to initialize two pointers. The first one's ESI is going to be initialized to point to the beginning of the array, and then the register EDI is going to be initialized to point to the value stored in D that we're using to initialize the array. So we then move the value from the XMM0 register into D array. So you can see right now D array is completely uninitialized. So we'll perform this one instruction, and you'll see now that we have initialized the first element in the array to 7.4. And next we're going to do this repetitive move S. So this is going to initialize the storage referenced by D array and pointed to by the EDI register with the value stored in D that's pointed to by the ESI register, and it's going to do that for count of ECX, which is now 18. So let's go ahead and execute that instruction. And so now what you'll see is D array is now fully initialized as a result of that repetitive instruction. So if we look at this code, it's really quite efficient. We had a loop that we've eliminated through the use of this repeat move S instruction. And so the reason we were able to do this was because the bounds of the array or the loop counter was known to be constant through execution of the loop, so there was no possibility it would change in the middle of performing this move S instruction. So that gave the compiler the latitude to generate this series of quite efficient instructions. So let's go back now to the source code, and we're going to do this next example, which I called scary array, because this is some really scary code that even though it's going to work correctly in this case, it's probably not the sort of thing you want to do in your code without a lot of comments and explanation. So we're going to call F2, and I'll show you F2 in a second. We're going to pass it 3 arguments, and so this is really parallel to the F1 function. The first argument is going to be the bounds. The second argument is going to be an array of struct S, and then the third argument is going to be just a single instance of struct S. So if we look at F2, again, F2 is very similar to F1. So in F1, we were initializing an array of double to a particular value D. So in F2, we're going to initialize an array of struct S using a single value for struct S passed in this lowercase s variable. So the function, again, looks very similar to the previous function. We have a loop where the loop is bounded by the value of the object referenced by PI, and we're going to move the value stored in S to each location in the array referenced by PS, and then of course we'll increment PS and then initialize the next element in the array. So let's go ahead and go back to our well, let me show you one more thing and then we'll go back to the assembly code. So again, we're initializing S to the value 0, so in fact we'll be just clearing out the array with these values 0. But the really scary part of this is that we set the last element in the array to this value 1000, and then we pass this value as the bounds. So we know, if we look at the declaration for scary array, that scary array has a bounds of 10, but here we're specifying a bound of 1000. So this seems like a really, really obvious buffer overflow, and that really bad things are going to happen, and that's why I call this scary array. But it turns out that this call is actually going to be safe. And maybe we'll just step into it to see why. So here we are back in the assembly code. We're about to just initialize s.a to 0 and s.b to 0. And now we're going to load EAX with the address of scary array. So we're now, again, this function has been inlined here, so there's no explicit call. But we're going to initialize EAX with the address of scary array. So this is the array we'll be initializing. We're going to 0 ECX. ECX is going to serve as our loop counter. And then we're going to move the value in EDX into the storage reference by EAX. And you can see here that here's our scary array. And the scary array is completely uninitialized. So when we do this move, we're actually writing now to the A element of the struct, so it's assigned the value 0. This second move instruction is going to set the B element of the struct, so we've now initialized the first element in this array. So we can increment the counter from 0 to 1, and now we're going to load in the new address and do a comparison to see if we've completely initialized the array, and if not, we're going to jump back. And so you can see now this subsequent series of moves is going to initialize the second element of the array. We're going to increment x, and we're going to continue along the way. So let me show you. Let me show you the bounds, which is stored in memory. So the bounds is stored at this address, -8. So I'll take this address and we'll look at the memory at this location, -8. And so you can see that we have this value, which is actually in Little Endian format. So if we look back up here in the code, when we initialize scary array to have a bounds of 1000, in hexadecimal that value's 3 echo 8. So you can see here in memory, we actually have the value 3 echo 8 in Little Endian representation. So I'm going to continue back through this code, single stepping through this code, and what we're doing here is continuing to initialize this array of 10 elements. So we're going to have to go through this loop 10 times, and let's just keep an eye on this value, because we know we're writing into this array which was passed as the argument. And here on this last iteration of the loop, we actually overwrite the bounds with the value 0. So now when we do this comparison and see whether we have to continue writing to the array, it turns out that we don't. So at the last second, I'll go back to this call. At the last iteration of this loop, this assignment actually overwrites the same storage which is referenced by the bounds, allowing this loop to terminate. So the only reason this works is because PI, of course, is a pointer to an int, and in the F1 function, PD, which is a pointer to a double, cannot be an alias to a pointer to an int. So we know in compiling this code that PI, the value, the object referenced by PI is loop invariant. However, in this example,
PI is still a pointer to an int, but PS, which we are writing in the loop, is a pointer to a struct S, and struct S has two fields which are both integer fields. So this means that that PI, having type pointer to int, can actually be modified by a value that has an aggregate type, including a member of type int, such as struct S. So the result of this is that PI, the object referenced by PI, has to be reloaded for each iteration. And on the 10th iteration, given the way we're using it, the value of PI becomes 0. That allows the loop to terminate. So this is, the requirement for how this code has to be generated, which is what makes it work. So if we look at the disassembly again real quick, you'll see that the result of this is a considerably less efficient implementation where we have to loop over a series of instructions. Whereas in the example where the bounds was loop invariant, we really were able to generate a sequential series of instructions to perform the operation, including this repetitive move, which was much more efficient. So this doesn't necessarily mean that one thing is right and one thing is wrong. It's just necessary that you understand the rules concerning aliasing, so you'll know what behavior to expect in each case. Most compiler optimizations will improve your code, while some might introduce unexpected and unwanted behaviors, such as the out-of-bounds writes that we saw in the sub-lessons in this section, and also other unwanted behaviors such as infinite loops. The key is to avoid undefined behaviors in your code, even if your code appears to be working for the time being. Undefined behavior is to a certain degree a portability problem, but it involves portability issues between even maintenance releases of the compiler you're using, where code that worked fine on an early release of the compiler might not work in a future release of the compiler, and it's not the compiler's fault, really. They have the license to do whatever they want with that code because it's undefined. So it's important to find and eliminate dead code yourself instead of letting the compiler do it. Dead code is an indication that something is wrong. So in most cases, programmers don't write code that doesn't do anything. I mean, there might be some special cases where for a particular platform you want code to not compile, but when you see that as being dead code, you'll recognize it and understand that it's meant to be dead code. But in most cases, again, it usually comes as a bit of a surprise that code you've written isn't actually doing anything. So, the recommendation is don't get turned off on optimization. Go ahead and optimize your code. You should try to use compiler diagnostics such as wstrict overflow to determine if the compiler is optimizing the code based on assumptions that are different than your own. In many cases, you can then rewrite your source code to more closely resemble the optimized code and eliminate these warnings.
Thanks for watching these live lessons on Professional C programming. In these lessons, you learned about integer types, conversions, and operations. You learned about the character types, arrays, and strings. You learned several approaches to string handling and how to select between them. You also learned about undefined behavior and compiler optimizations. I hope that what I've shown here lets you improve the quality, safety, and security of the C language programs you develop. Remember, if you are interested in accessing the source code for the programs in these lessons, just click on the Extras tab to download the zip file. You may also be interested in the Cert C Secure Coding Standard available from Addison Wesley or from our Secure Coding Wiki at www.securecoding.cert.org. And if you're interested in live training courses at your company in C language programming or in other subject areas, check out our website at www.cert.org/securecoding. You can also send me an email. Good luck and have fun with your newfound mastery of C language programming.